Okay, guys and girls, thank you very much to Daniel, who did a fantastic talk about Takahashi. Up next is going to be Adam Block with imaging at 9,000 feet. This is going to be a very, very science
Okay,
orientated
guys and girls, thank you very
interview,
much
for a lack of a
to
better
Daniel,
description, or a
who
presentation. So
did
this
a
should be
fantastic
pretty
talk
damn
about
interesting.
Takahashi.
I got a sneak
Up
preview,
next is
just so
going
you
to
guys know,
be
and
Adam
God,
Block
there's some really cool
with
stuff coming up.
imaging at
So
9,000
we're going to
feet.
be starting at 2 o'clock.
This is going to be a very,
Make sure you come
very
back. The stream
science
will carry on
orientated.
running. So if you guys got questions and
Thank you
things
very
like
much
that,
interview, for a
just
lack of
feel
better
free to start
description or a
firing them up,
presentation.
and we're going
So
to be
this should
back
be pretty damn
in
interesting.
just a moment.
Up
See you
next
soon.
is
Just so
going
you
to
guys know,
be
and
Adam
God,
Block
there's some really
with
cool stuff.
part of the challenge that the amateur astronomy community is facing is to bring in more people into the hobby. So we've been actively trying to contact different people, science communicators, people with influence are also interested in astronomy, to help them help us popularize the hobby. I think it's very, very important for all of us to do that because as a hobby, we want to make sure that it's growing. And one way to do it is reach out to younger people, make sure that the next generation, the younger people, are actually getting into the hobby.
Basically, I look at it now and I think of astronomy as more of a really artistic. You look at all the beautiful pictures that they do, and I think that's going to bring more people in. It's like getting the big buck for the hunters. You want to get the most beautiful picture that you can get, and it's kind of a competition, really. Something that can be achieved, and you don't have to have physical strength. You don't have to have all these different things, but you can go in and just be able to have that creative spark and eye, and go out there and work with it.
I guess what I do is I have a small group of friends near my home, and if I have a night where I decide to take out the telescope, I'll invite them along. It's not really their hobby, but it's nice to branch that out. But I would like to do some outreach to some high schools or elementary and get the kids interested early so that it's not something you're starting when you're 20s or 30s. It's something you start early on and you just get that for your whole life.
Already we can see that the impact of social media has popularized astronomy a great deal amongst people who just have no real direct interest in astronomy, but they get excited about these things, like this eclipse that just occurred. Had one of the largest turnouts that have ever occurred for a solar eclipse. And I think it's 100% due to social media and the news coverage that it gets. So I think that is making it more important. In other words, you can reach people much easier now than you ever could before.
I think the general public is more into the now results. So a lot of people like to share things. I find that people like sharing. They want to see results. They want to make things easy. So I see a expansion into just easy imaging and sharing.
There's a lot of people now doing science, not just astrophotography anymore. There's a lot of people doing science. There's a lot of citizen science, and there's schools that are doing science. The easier we make the telescopes, the more science that the schools can start doing. We get colleges doing science, and maybe even down to high schools doing some science projects with NFS grants and such. So because the capabilities of the telescopes today are so much more, I think the way to get the young people involved is to get them using them in schools.
On the scientific point of view, astronomy is trying to answer very fundamental questions, and most of them have to do with cosmology, meaning where does the universe come from? And there are still many questions. Most of them are unanswered. The other search, I think, in astronomy is searching for other planets, other intelligent civilizations, or even sign of life, simply sign of life on other planets. I think that's the second quest. The first, I believe, should be trying to find out, answering the big question of cosmology today.
I think there's a renewed interest in astronomy. It really peaked for our generation, or the generation slightly before us, with the moon landing and the Apollo program. And then we had the space shuttle, but with the cessation of flying the space shuttle, people predicted that there would be less interest in astronomy. But as Cassini and some of the other probes have demonstrated, a lot of interest is generated because we're getting looks at our solar system with the technology that has been put into these probes that we were never able to get before. And I know that the generation, my children's generation, has a lot of interest in these types of things, and I think that interest will continue. And those are the future astronomers and future amateur astronomers that are coming out of that.
I think what you're going to see, and what you're already seeing, is that amateur astronomy is making significant strides in the professional realm. You've got amateur astronomers finding comets and asteroids and near-Earth objects And I think that's just going to continue to happen. I see a network of astronomers, maybe a network of satellite imagers. You know, if you can turn households into a satellite spot, and suddenly you've got a satellite telescope that's the size of a hemisphere, you know, just because amateur astronomers are working together. I see that happening. I see the entire community coming together and doing more.
In terms of making astronomy something that it can reach a much broader audience, you know, we want to see more development of those accessibility options via the internet and ease of use, to try to make it a simple process. Using your iPhone is a pretty easy thing to do, and it'd be great if we can get to where people can access these high-end telescopes and take these terrific images and also do research. You think about the science projects we did when we were young, you know, in some respects pretty primitive what kids can do today.
You know, one of the most successful programs that I've seen for engaging younger students and younger kids in astronomy is the Sonoma County Astronomical Society has a program where they have students, little kids, like write essays, and then they take the best essays on astronomy and they give them telescopes. And these kids, I've been surprised, it's mostly girls. These kids, they get these telescopes, they bring them to star parties, and they become little experts, little amateur astronomy experts, and they give public talks and presentations, and this is one of the most successful places. I'm a member of about 5 different astronomy clubs, and this is a great way to bring in a younger generation and help them maintain it, because we've seen over years now these kids come in and they stay in there, and this is a kind of program I think we need to scale it, we need to use it as an example and do it elsewhere, just sort of one small example of one thing we can do.
We live in a fast age, right, where our movies and our music, our media, you know, fast edits, instant gratification, loud and in-your-face kind of stuff is required to hold people's attention today for a half a second, which is sad. And so the subtle and the esoteric stuff suffers. I think it's very difficult to get a lot of younger people into this as a hobby. It seems like there's more younger folks, even women, who manage to get into the professional sciences, astronomy, cosmology, whatever it is, but in the amateur way, getting them to a telescope, getting them to a dark sky, inspiring that wonder in them, it's difficult, I think.
Giving someone the opportunity to not only see it for themselves, but do it for themselves, and say, here, you know, have a look. If, for example, if they have the privilege of looking through a telescope and seeing the rings of Saturn, give someone that opportunity to do that and see it for themselves with their own eye. It has an incredibly powerful impact. And what I'll find, and for those who, like I say, there are many outlets where you have an opportunity, city star parties, outreach events. Once you see it for yourself, it's like a catalyst that the rest starts to take care of itself. The interest will be there.
One of the things that concerns me greatly is the fact that so many people are moving away from science and from facts. The fact of the matter is math, history, science, and facts matter. And so to advocate that and to advocate education, I mean, I believe that college education should be absolutely free. We should be investing in the brain trust of this country. And so to me, our job is to advocate science. Our job is to inspire people to really embrace what is right.
The stars are for everybody. And I would like, if I could do that, if I could spread the interest out amongst everybody, that would be the biggest contribution I can make.
All right, guys, We are back and we are going to be introducing Adam Block. If you guys don't know who he is, why are you here? You should know who he is by now. So, without any further ado, I introduce to everybody Adam Block.
Hello, everybody. How is the world out there? I'm going to attempt to share my screen.
Ooh,
so thank you very much for the opportunity to speak today. And this is on a topic that I'm really excited to talk about. So I'd like to talk a bit about the astrograph that I use on top of Mount Lemmon, which is just behind or just north of Tucson, Arizona. And I'll be describing both the science and the art that I do with that particular telescope. So that's the subject of the talk. There is one picture I want to get out of the way right now, although we did arrange that you can see me live. There's another version of me there. That's it. Beyond that, what I'd like to do to introduce this particular talk is show 2 videos really quickly. The first will kind of just give you a sense of the kind of science that the astrograph is doing in a pretty way. And then the second video will show you the results of some of the art that can be done as well. So I'll turn it over to Simon for a moment. So right there at the end of the video, you saw two telescopes, the smaller one being the one that will be the main subject here, though I'll be showing you images that were taken through both telescopes as part of this talk. They're kind of complementary to one another. So in this presentation, what I'd like to do is begin actually with the science and go through what is the measurement of the brightness of the night sky, that is the photometry of the night sky. The telescope is also used for what would be called space situational awareness, basically the characterization and study of satellites that we put up there, the ones that we make that orbit the Earth. And then there's another subject which is kind of interesting, not something well studied, but deals with the moon. And then I'll go into some of the pretty pictures showing some of the art that is possible through this telescope. And given some time, I may even show a few what I would call vignettes of image processing, just a few examples of what makes the images look like they do, especially with regards to the astrograph. There are some things that are part and parcel to wide field imagery, and that and elements of image processing help to make those images look the way they do, hopefully look compelling and captivating. So this is the astrograph in its very beginnings. There's the salient detail and information about it, indicating the focal length, the camera that we're using, and most interesting, the plate scale. This is a very fast system, so the field of view is on the order of 4.5 degrees with almost 5 arc seconds per pixel. So this is not meant for resolution. We're studying basically the brightness of the night sky, which requires no resolution. And then there is also the study of satellites that need only be detected at some level. Again, no resolution necessary. For pretty pictures, it's nice, but that isn't the point of this system. It's wide swaths of sky. This is the enclosure. So let me just have some shout outs here. First of all, the astronomer who's the primary investigator of all of this, his name is Dr. Eric Pierce. He works at the Department of Astronomy at the University of Arizona, where I work. And so it is through his funding and in some sense generosity that all of this takes place, because there's the science that he wants to do, but then he also gave me the ability to do some public outreach by allowing me to populate this very nice filter wheel with a few broadband color filters. And that allows me to take the color imagery. Also, another shout out to the gentleman who basically built this enclosure and much of the innards inside to make it possible to automate, which is what I worked hard to do. His name, he's a graduate student, Harry Krantz. So shout outs to both of those members of the team that have really been huge in making all this possible. So we visited a number of sites to measure the sky brightness. One of the places that we took this, you can travel around with it by dragging it behind a truck, is Kitt Peak. So this is Kitt Peak National Observatory. You saw the video, that's what it was featuring here. And what it showed is one of the kinds of observations where you basically raster across the sky to make these measurements of the sky brightness. So I'll be getting back to that shortly, but there are some more, there's my video, I embedded it. There's some more technical details I'd like to mention about the telescope and what it does that will help understand that science. And here is where it actually is right now on top of Mount Lemmon. There's another set of observatories that the University of Arizona maintains and operates on top of the mountain there. This also houses, I should mention, in the background there is Catalina Sky Survey. They are well known for their detection of near Earth objects and often the discovery of other comets as well. There's another video. To give you a sense of the field of view, here is the Andromeda Galaxy with the moon placed within the field. Now, this is actually an old picture, but it was taken with basically the same telescope many years ago, and I just put the two together. But it just gives you a sense of scale so you can appreciate how much of the sky we're able to kind of swallow or gulp with this particular telescope. And as a reminder, I'll be talking about magnitudes, that is the brightnesses of things. Here's a scale which kind of outlines a few of those numbers. Brightnesses of things in the sky, the bigger the number, the fainter, of course, they are. The magnitude scale goes in the opposite direction, and it is logarithmic. So these numbers increase rather dramatically when you go to one side or the other in terms of brightness. So with Pomenis, for example, which is the name of this astrograph, it's right here on the right next to the Schulman telescope. That's the other telescope that's at the Sky Center. So Pomenis is a 0.18 meter telescope. Schulman is a 0.8 meter telescope. HST is a 2.5 meter telescope, but it's in space. So you can get a sense of, with typical amateur telescopes, the kind of range of faint limit that you can achieve with them. HST being in space and a relatively large telescope can do really quite well. So where I begin in terms of appreciating the kind of science that you can do to study the night sky, you need to appreciate what the sources of sky brightness are. And there are many natural sources of this brightness. They include scattered light from the stars and moons, the moon, the Milky Way and stuff like that. More interesting though, that's the kind of the natural glow. There's also this air glow, that is our atmosphere. Molecules in our atmosphere are excited every day. And those things, I'll show you some pictures, glow during the night, through the course of the night. And that's a very large component of the brightness of the night sky. There's also zodiacal light, aurora, and so on. So let me take those in turn here. Air glow is really kind of strange. I'll be showing you the spectrum of it in just a moment, but it emits light in various wavelengths. And if you take a picture, such as shown here, this is a beautiful picture by Miguel Claro. It shows the banding of this air glow in the upper stratosphere and how it's emitting different wavelengths of light. I hope, I've never been able to take this kind of picture, but I hope to be able to do so now, because I just received from Woodland Hills one of these modified Canon cameras. So I'm very excited to potentially give that an opportunity to do a picture like this myself. Zodiacal light, I have been able to see, and even from Mount Lemmon, this is the glow of light that you get scattered off of dust that's within the plane or the ecliptic of our solar system. And it backscatters light to us. In fact, in the direction that is exactly opposite the sun. In the night sky, you can get an enhancement of that scattered light called the Gegenschein. Aurora, of course, can illuminate and change the night sky brightness dramatically. Now, from this latitude on the Earth, it's extremely rare to see a very bright aurora, but auroral activity is always taking place, especially when the sun is active. This is actually a rare photo I took a long time ago, where there was an extremely bright aurora that could be seen from this latitude. Kitt Peak is roughly at 31, 32 degrees north latitude, very rare to see. I never thought in my life I would ever see an aurora from here. I thought I would have to travel, but I did not. It came to me, and it was really wonderful. So the filters that are in place in this system are scientific filters, the ones that are basically, well, both of these graphs show scientific filters, but the Sloan filters are the ones on the bottom are the ones that we are usually using to make most of our measurements. But we also have at the top graph there, one of the V filters, the Johnson-Cousins filter, that is also prominently used as a reference filter for making measurements. So you'll see me refer to these filters, and if you can somehow capture this in your mind, you can get a sense of what colors they are. It's not important. Probably the most important one to remember there is the V filter, which is kind of like a visual band, greenish light somewhat. Now back to that air glow. Here's another picture of it by Yuri Bedelsky. He took a wonderful picture that shows some of these lines that are being emitted by the Earth's night sky atmosphere, the upper atmosphere. The ones that are furthest to the right, the really red ones, have a name, and they are captured in that filter that one of those Sloan filters that I just showed. Sorry, let me go back if I can. That Z filter captures that particular wavelength of light. So I'll be showing you some data that I've taken through the telescope, and it actually shows that particular banding, and it's really interesting to see. So this is a major source of light in the sky. It was surprising to me when I first started to do this science was to learn that the sky was actually brighter in the red wavelengths than it was in general, in visual wavelengths, and that's just because of this air glow. That's crazy, but it is. So here's an example of the red emission that I took a picture of using the Z filter. I removed all of the stars so you can just see the banding of light. And this is when looking fairly low in the sky when I was at Kitt Peak, and it showed the banding very, very well. So one of the things that I'm trying to get across in this talk is something about the night sky. And I will just pose this question. I don't know if this will work in this format, but I'm going to pose the question. So this picture is a picture I took not through the small telescope, but the one next to it, which is a slightly larger telescope. It's a beautiful picture of some faraway galaxies. But this is something that is very interesting in amateur astrophotography. You have a picture that looks like this. There is something actually kind of wrong with the picture. And I just wonder, I'm going to pause for a second. Maybe we can just use Simon as my foil. Simon, there is something wrong with this picture. Do you want to take a guess as to what it might be? Maybe wrong is too strong a term, but it's being characterized in a way that isn't true.
I am not even remotely sure.
All right, so I'll tell you the answer and we'll see if anyone else was thinking of it. The sky is dark. I have displayed the image in such a way that the sky looks black. But in reality, what I've been trying to convince you is that there are many other sources of light, and in general, the sky is not dark. It is actually a choice to display it in this way. I think that the main reason we enjoy displaying pictures like this is because when we look with our eyes, which are not terribly sensitive, at the night sky, it looks quite dark, it looks quite black. And so we reflect, we mirror, we echo that in our images. Perhaps if our eyes were more sensitive and we were able to see more sensitively the night sky, it would be in a way that we wouldn't make our images so dark and contrasty as they are. I think that's actually a function of our biology in a way. It's a preference.
So a couple of people actually pointed out, clip the sky to black. That was from Christoph. And then Kevin also said sky background.
Yeah, well, it's not, depends on what monitor you're looking at. Now on my monitor, that is not actually black clipped. There is sky, but it is quite dark. It's a very contrasty image, that's right. Okay, so having said this idea of the sky having a brightness to it, it is important to measure that, because you have to appreciate what all the natural sources of light are, and then you measure it to determine maybe the sources that might be a polluting nature, an additive form of light pollution. That can tell us something about our effects on the sky, how viable a particular site is for doing astronomy, all of that kind of stuff. So to make those measurements then, you need to do a form of photometry. So the measurements that I made with this astrograph are such that, I'm going to look at this screen here. I surveyed the, kind of rastered across the whole sky in the following way. I took a picture of a patch of sky relatively low, and then I moved up in altitude, and I took another picture, and I moved up in altitude, another picture, and so on until I get to the zenith. Now, I only did like 5 or 6 of these measurements per one of these altitude lines, and then you rotate the telescope a little bit. You move in azimuth, and then you do it again, maybe 15 degrees, and then I go up the sky again, and then I move another 15 degrees and go up the sky again, and so on until I've circled the entire sky. So for a given altitude, I have a set of azimuthal measurements in a ring that go around the sky, and the density of that ring is just determined by the separation of my azimuth integrals as I go across, as I make my raster. So that's just to give you a sense of the observations that I was making. One of the things that you also need to know about the atmosphere, I guess, let me leave that picture back here, is that when you're looking through the Earth's atmosphere out into space, if you look straight up, you're looking through this graph does not show this very well, but you're looking through the smallest quantity of air when you look straight overhead. If you look towards the horizon, you're looking through much, much more air, many more air masses. If straight overhead is 1 air mass, then you might be looking through 2 air masses when you're looking at about 30 degrees. And then when you get down to 15 degrees, 3+ air masses. And when you look low in the sky, mathematically, it kind of goes to infinity. Of course, that isn't true, but it becomes many, many air masses, which has some effects that are important. Those effects, for example, is that it scatters and absorbs the light. There's a wavelength dependence to how that works, and you need to compensate for that if you're going to try to measure the brightness of the sky. The air glow, for example, might be either dimmed or brightened depending upon where you are looking in the sky. And so its contribution would be important to understand. The stars, which is what you're using to measure the intensity of the light as a reference, you need to compensate for what the atmosphere is doing to them as well. And so what you can do is the following kind of thing. You can make graphs like this. This graph attempts to show a relationship between what is called a 0 point and the air mass, the amount of atmosphere that you're looking through. So I'm going to break away from this and show you a quick little, kind of like a cartoon here. Here's what you need to consider so you understand where the problem is. In order to make these measurements, you need to compare what you're measuring to some reference. So there exist catalogs, astronomers who have made very careful measurements of stars in the sky. And by comparing your measurements of those same stars, you can calibrate your telescope, your system, to match theirs. And as long as their references and everything that they've done is understood, you can transform your measurements into their system. And then when you publish a paper, everyone will agree about what you've measured. And about in this case, the brightnesses of the sky will be understandable. So we need to get the measurements out of what are called instrumental values, that is what I measure with my instrument, but that might not match up with anyone else's for the following reason. The typical way that people make measurements of some reference system is they pick, now they don't do this today, but it used to be that you would pick a star and you'd say, that star we're going to call like 0 magnitude. It is our reference star. Today, you'd use a set of stars and you do fancy math and you come up with a reference system, but it is arbitrarily chosen as a reference. So it used to be Vega. Vega's not a terribly good reference star because it's actually a variable star, but let's pretend it's a reference star. So if I have, instead of a single telescope, what if I had 2 telescopes that are maybe side by side? So I have my telescope and a friend's telescope, and we're both looking at Vega. Let's not call it a friend. This is the professional astronomer, the first telescope here. They're the ones with the reference catalog. So if I match my telescope, my camera, everything, and we both observe Vega at the same time, we should get the same brightness of the star, and we can just arbitrarily say, hey, it's 0. You measured 0, I measure 0. It's 0th magnitude. Everyone's happy. But if I'm using a slightly different telescope, maybe with a different camera, different filters, and so on, the measurement that I make, the brightness that I get when I use my instruments is going to be different than what the professionals have, just because I'm using different detectors. You can also have the following problem. Not only could I be using, say, a different telescope, but let's say that I got there late and I started making my measurements of Vega not when it was high overhead, but instead when it was lower in the sky. Not only am I now using different pieces of equipment, but I'm also looking through a different amount of air. All of that gets folded into what I would measure. So what I end up doing is I compare my measurements to this catalog that the professional astronomers have made, and then I compute that relationship. I can actually fit a line between my values and the astronomer values, and I can say, okay, here's my magnitude, what I say my instrument has, here's the magnitude in the reference catalog. So I can say, okay, here are the magnitudes that I measure, and I'm done. It's just not quite that easy, though. One of the major things that you need to compensate for is actually this air that you're looking through. Because the measurements that the astronomers make when they publish those catalogs, they remove the contribution of the air that you're looking through. It's as if you were in space or something. That's the colors and that's the brightnesses that they put in their catalog. So I don't have that. What I have when I make these observations is something that looks like this, where for every each of these little separations here, those are my altitudes basically. And so as I go around in azimuth, I have a big smear of different values that I measured. It's the same altitude, but at different azimuths, and they all look kind of scattered there. So it looks like the sky has different brightnesses as I went in a ring around the sky. That's what it looks like, but hang on. And when I fit my line, that is, when I fit the stars that I measure to the catalog, I get something called a 0 point. You can basically draw back on this fitted relationship and you can say, what's the minimum brightness that I could observe with one little count of my detector in some little period of time? There's a number that gets associated with that. Their catalog, the reference says that should be a certain brightness. And so when I graph it here on the chart, I just get a number. It's called the 0 point. The number itself doesn't matter. It should be very faint, but the number itself doesn't matter other than it's what I get spit out to me. When I do this analysis of the images, what I get are 0 points at every position in the sky that I observe. And I can use that to my advantage because what I can do is I can plot the 0 point that I get from the measurements compared to the amount of air that I'm looking through, the air mass, and you can draw a straight line right through those points. And that gives you the correction, the coefficient of extinction, all sky coefficient of extinction, the correction you need to apply so that you take out the effect of the Earth's atmosphere. That's all this graph is allowing me to do. It's removing the effect of the Earth's atmosphere, and you have to make this measurement so that then you can say what the brightness of the sky is at every point that you looked up there. Now, this was interesting because the way in which you do it, this graph just shows that the sky has different degrees of this extinction, this effect of air mass, depending upon wavelength here. So you can see the lines are not all the same. But what you do in your data when you make this measurement, you have to compare your stars to the reference catalog. And so what you do, these are stars in my image, and you make a little aperture around the stars and you measure them. You measure the flux, you measure the amount of light that is there for many stars, and then you compare them to this reference catalog. But the way that the program works that we were using, it's a pipeline that processes all this information, it was automatically choosing the aperture for what it thought was optimal. And so this graph that I showed you here before, what it signaled to me is something that intuitively I didn't know a lot about. This is not my area of expertise. So by the way, everything that I'm saying right now, I hope most of it is true. It may not be entirely true, but I hope most of it's true. One of the things that this graph communicates is that something was varying. As I said, I pointed around the sky at some given altitude, and for some reason at that given altitude, I had a whole bunch of different brightnesses of the sky. That seemed weird because when I looked at my data, it seemed like the data was very consistent from image to image. And there was nothing about the system that was changing dramatically. It just didn't seem to me that the graph was matching intuitively what I felt the data was communicating to me. So I searched for sources and I found this idea, once I understood what the processing was doing, that it was dynamically choosing, based on its algorithm, this aperture. And it turns out that if the aperture is too small, then it messes up that measurement of that photometry. So this happens to be, I think, a special case when you have undersampled stars and we have stars as small as what you see here. That can be a problem when you're doing this aperture photometry. So if you make the aperture a little bit larger, where you are now sampling a little bit of the star and the sky, things become much better. And this for me was like a really red letter day, because I asked the program, please show me, don't automatically calculate your aperture. Show me what the aperture, what you get when you have the aperture ever so slightly increasing. I want to see what happens to the photometry. Does it change? And the answer is it did. Check it out. So this is what it looks like when the aperture was 1, which is about what it was choosing, which was not very good. And then you go to an app, well, let me just do, that was too dramatic. So that's 1, and then there's 1.5. Do you see how the points get a little more clustered? And then you go to 2, and they look a little better, and maybe 2.5 might be somewhere near the best. And then 3, probably the larger you make that aperture, when you start to include more sky, maybe the noisier it'll eventually get, because you'll start getting other stars if you make the aperture too large. So instead of dynamically choosing the aperture, I forced the program to choose an aperture that I thought was a bit better, and that was near that 2.5 range. And that was huge for me. Oh my goodness, that means that the values that I was outputting were correct, or certainly better than they were before. In fact, the information became so good that, I don't know if you notice here, this line that's drawn on the chart, it's terrible. I only discovered that the lines that I was drawing, I had a mistake in my program, my graph, were incorrect once I bettered the photometry, and then I corrected it later. So this is what it looks like when you actually kind of do it right. You get a nice fit of points along that line, and that correctly characterizes the correction that you need to make for the air mass so that you can calculate the brightnesses of the night sky. And this is what it looks like when you make all the measurements. I wrote a very long program to ingest this data and then plot it in this kind of polar plot. And so these are the values in magnitudes per arc second squared. And it tells you how dark the sky is. This is actually Kitt Peak. And Kitt Peak, when you're looking straight overhead, looks quite dark. Now you might notice something though. Some of you that might have SQM measurement, SQM little devices, you point at the sky and you say, well, I have 22 at my site. One of the interesting things is when you're on top of a mountain, it is easier to see the air glow because you're looking through less atmosphere. And so the sky actually is a little bit brighter when you're higher up in the sky than it might be when you're lower. And of course, the sky, the air glow varies from night to night and so on. But in the literature, these values are actually quite good for the National Observatory, even compared to those values maybe a decade or more ago. So, you know, getting there in the mid 21s. And then what's interesting, if you look at the Z band, this is where all that air glow really shows its ugliness. Look how bright the sky is. It's like 19th magnitude per arc second squared, but several magnitudes brighter than what it looks like in the visual bands, which is kind of interesting. And then this is actually what it looks like from Mount Lemmon. You'll notice that at the bottom left and the bottom, that contribution is from Tucson. So you get a glow of light there more towards the south. But straight overhead, you'll notice that it's actually quite dark. The extra elevation, 9,000 feet, Kitt Peak is only 7, I guess helps a little bit. Straight overhead, it is almost as dark as the Kitt Peak can be. But of course, if you go anywhere else from straight overhead, the sky, of course, becomes brighter because of the contribution of the city. And then here's the Z band. You can see again, the sky is quite bright on this night, showing whatever that air glow is that goes on up there. This is just a chart which shows from some time ago the changes in the sky at some of the sites that are here in the Southwest sites that we visited with this astrograph to make these measurements. And you can see they do have a column here that's for V. So those are the V numbers, and they're very similar to what we had measured. And of course, I found that very encouraging. And you can only do that after you make all of that correction stuff that I was talking about. So that's what I really wanted to indicate about the sense of doing some science, just to give you a taste of what you need to worry about when you're making these kinds of measurements. This is my attempt at doing something else kind of fancy. You can take the difference of 2 of those runs of measuring the sky and take the difference between them. So for example, if you wanted to know what the city lights are doing before and after midnight, how businesses might shut off their lights, or maybe the street lights are still being a problem because they're coming on, you can make measurements at the early part of the evening, later in the evening, and then take the difference of the 2 and see what the sky is doing. And that might give you other kinds of information. This is the last one of these polar plots. I'm very proud of these things because it's hard to make again. This is actually from the rooftop on campus of the Department of Astronomy, the building on the rooftop. I made a measurement up there as well. And what's interesting is that, does anyone want, this is for Simon, my foil. Here is a picture of the sky, and here's another picture. Notice what happens in this case. The darker color means darker sky. So it's relatively dark here, and then something happens here. Actually, time-wise, it's actually this, and then it went to this. So it started like this, and then it went to this. You want to venture a guess? I'm on campus, what that might be?
Somebody probably walked past the security light and tripped it off.
It's bigger than that.
Oh, it's bigger than that.
Yeah, that's the stadium. That's the University of Arizona stadium lights. There's a stadium that is east of the building. And when they had the lights on, the sky looked like this. You turn off the lights and the sky looks like that. Even from campus, it makes a big difference. Okay. So that was my little personal story. I cannot tell you how pleased I was to try to find out, something about how the program was working. You needed an understanding of the stuff about the physics of the sky and the stuff about how the program works, and put it together and say, we really got to test that. I don't believe it. And sure enough, that was the answer. So there is another element of the use of this telescope, which is for what's called space situational awareness. It is the study of satellites. And I'd like to show you just some quick examples of that. This is a chart which, this slide rather, kind of gives you a sense of the motivations for this kind of study, to provide rapid capability to discriminate between the different kinds of satellites that are up there. You got to keep in mind, not all satellites are currently maintained. After some period of time, they might just be floating around up there and lost to the, because they're no longer maintained. They might be tracked and you have to keep track of them and so on. You got to know which ones they are. You can also, and I like how this is put here at the bottom, under potential scenarios, no, actually under general capabilities, it says allow for rapid discrimination of multiple objects. And then under potential scenarios, discriminate solar panel covered microsatellites from debris after an on-orbit event. That sounds very euphemistic to me, an on-orbit event. That doesn't sound like something you in general want to have happen to your satellite. So here's now this will be interesting if this plays and looks well. I might ask Simon for verification. Here are some satellites. All I'm doing, these are geostationary satellites. So I've turned off the drive to the telescope. And here's another one. This one actually is not geostationary, but watch what happens to it. It's going to flash at you. Did you see the flash? Let's see. I'll do it again. It's a flash there. Oh, maybe I got to go back a little more. Sorry. There. So it should flash very brightly there. That is a specular bit, probably some bit of the satellite, but based on the brightness that you can see here, that would have been observable by your unaided eye. You would have actually seen a little flash for just a brief moment from this satellite, which you wouldn't have seen with your unaided eyes otherwise. The satellite is called Sirius. The other one, I think, were the Galaxy set of satellites. There they are again. Right. And this is something that my colleague Harry Krantz did just recently with the astrograph, is he took a picture of TESS. Now, unfortunately, it's ephemeris. It's coordinates at a particular time. You need to know the rates very accurately, and they were not known for us. So that when we tried to find it, when he found it, it doesn't look like a little dot. It looks like a little smear. But the interesting thing about it is that this is an interesting satellite. I encourage you to look it up. It does some cool astronomy stuff. But it's at this point 200,000 kilometers out there, and you're able to detect it with a tiny little 7-inch telescope. So it's kind of cool to be able to do that kind of work. Now, the part that I think is topical is this idea of you have these satellites in the sky. We live now in a world where we're putting up satellites everywhere, and they cross the sky all the time. When they're far enough from us, they're always being illuminated by the sun. So geostationary satellites, for example, when you look in the night sky, there's a band of them basically going along what is the Earth's equator projected into the sky from the equator anyway. So for us, we look down on it a little bit in our northern latitude. And you would see just all of these satellites if you had really sensitive eyes. I'll show you a picture of that in a moment. But when you combine images, you wouldn't necessarily want to see all of those satellites. I'm going to close Photoshop here. Oh, you're not supposed to see that. That's okay. And I have to find the correct slide here. It's this one. What I have here is a picture, and this is the quintessential example of the Orion Nebula. Now, these have been there for years, right? These are just geostationary satellites. And as the telescope tracks on the sky, because of the Earth's rotation to track the Orion Nebula, satellites will look like lines passing through the field. So if I blink through the images, does that show up, Simon? Do you see the lines going across the frame?
Oh yeah, it shows up really well.
Okay.
Looks like column defects.
Yeah. If I blink through the frames, it looks a little bit like Star Wars. Do you see how they're crisscrossing everywhere? So all of those, if I co-add all of these images together, all of those lines are in all of the data. So what you want to be able to do is reject all of that information. Without rejecting it, what you end up with, I'm doing the wrong thing. What you end up with is good. Is you end up with a picture that looks like this. This is the co-addition of all those frames, and you would end up with all of those satellite lines going through the image everywhere, which looks kind of terrible, right? So that isn't what we're shooting for here. Instead, let me be sure I can go back. We'd like to be able to reject all of that information. So I apologize if this has been on the screen. You should tell me that kind of thing. Okay. Let me just show you something quickly, what it looks like to reject them. I can simply combine this information using image integration, and there is a mathematical way. Be sure I'm in the correct directory here. It looks like I am, star red star. There is a mathematical way of rejecting, oh, I know what I should do. Star M42, star red star. There we go. Rejecting all of those satellites. And I'm literally going to do this on the fly for you, just so you can see it. The method is the following. You tell it you're going to average all the images together, but statistically, you're going to choose a way to reject them based on some, what's called sigma tolerance. You're going to look for every pixel, you have a number of measurements, and then you're going to say if these measurements are much, much greater than the average, we're not going to include them in the average. And that is what these values here control. So I'm going to pick something that's kind of reasonable here. Oops. Like that. And we'll tell it to do the job. You just give it a moment, it'll do it, and I'll get a chance to get a drink. And here's the result. What's most interesting about this result is it gives me a map, a picture of everything that was rejected, and you can see all of the satellite lines in the rejected values. And so this is a mathematical way. I'm not doing this, by hand in some way. That's a mathematical way to remove them so that the final image, of course, shouldn't show that information, or shouldn't show it well anyway. And you get a good result for your color picture and things like that. I'm trying to stretch this. I'm not doing a very good job here. So the final result of an image that looks like this, let's do this. I was on it. It's something that looks like this. Now this was actually taken with the astrograph recently, this past winter. And you don't see, I hope, the evidence of the satellite trails, but yet I am able to display all of the faint nebulosity down to the very limit of what this telescope basically can do with the data that I got from it. So just another quick thing where all those satellites are coming from. One of the interesting things that I did is I took a picture. It wasn't even with the astrograph, but it was with just a simple long lens and a DSLR camera of the entire geobelt, or that was available on this night. It's not the entire geobelt, but that was available on this night. So this picture, oh, I thought it had already loaded. Sorry, it's a really big picture. It's loading here, but it just goes across the sky. So this is about 60 degrees or more of sky. And I stitched all of the pictures together so that if you zoom in, you can see that, and this is something that anyone can do because you don't need a track. You just point your camera at these different pieces of sky and you take pictures with a relatively long lens, and you'll see these little dots show up. Each of the little dots, if you're looking along where these geostationary satellites are, there, every one of them is a satellite. And I went through and I labeled them all. In fact, I should have paid attention. The galaxy ones that I showed a video of earlier that were kind of clumped together, they are here, also clumped. There's Echo. There's some more galaxies, but there was a group of them. Yeah, I don't know where they are. There's a Sirius thing. No, I'm not kidding. It's Sirius. Okay.
So for those people who are watching this,
yes.
A lot of those satellites that we see up in the sky is actually what gives you your television, oddly enough. Most of the galaxy satellites out there are all the TV channels. In fact, if you can actually get an antenna and point it, you can actually see CNN from, say, New York if you wanted to.
Yeah. Let me just show you one more thing that might be of interest to amateurs. If you like these satellite things, you can take pictures of the sky and then you get a satellite in your frame that looks like this, right? I'm using Maxim DL, but satellites, they're not stationary, they move and they rotate. So one of the things you can do is you can graph that, the rotation through time. So I can draw a line here. This is using the little graph tool in Maxim DL. And if I match this line very well, let me try here. See, if I just draw it across a random piece, you just get kind of noise as it passes through stars and other things, right? But if you go along the satellite, I'm trying, something like that, you get this very nice regular pattern. And you could actually make measurements, potentially, of the rotational rate of the satellite and other things just by drawing that little graph line across the satellite trail. I don't know, kind of fun things to do if you get satellites and you're so unhappy to see them in your frames. Well, make a cool measurement, make a graph of what they're doing. It's kind of fun. I'm going to close this as well. There. Okay, so let me try to get back to my presentation. So that was the Earth's equatorial belt. It's kind of like our rings on the Earth. It's by man-made stuff. So one last topic here concerning this science that's doing. You now know, the study of the night sky brightness. There's the satellite stuff. Well, there's another topic that requires an understanding of both, and it deals with the moon. One of the interesting things about the moon is that it could serve as a place to orbit satellites about. So there are some satellites running around the moon right now, and you could potentially do this because you wanted to have some kind of service that makes sense from a lunar orbit. Maybe you're studying the moon, or maybe you have nefarious purposes. I don't know. But if you did, there are particular orbits about the moon that make sense in terms of cost savings and energy and all kinds of stuff. So the little orbit diagram that I've drawn there around the moon kind of gives you a sense of scale of where in the sky, literally near to the moon, satellites would appear as viewed from Earth. And so you can imagine if you wanted to study or keep track of satellites that are orbiting the moon, you would need an understanding of the brightness of the sky, because when you look near the moon, the sky is very, very bright. And of course, you need also an understanding of the operations of satellites and motions and detecting them and so on and so forth. So it's a combination of those two ideas. So this is kind of giving you a sense that if you wanted to observe these things, the moon is not always available. As it orbits the Earth, you're going to get different geometries and different times when it's available and not. And so it might make it easier or harder to see a satellite and so on, or something that's orbiting the moon. But one of the studies that we've been doing with this astrograph is kind of trying to understand the brightness of the sky near the moon. There are people who have studied this, not many. It's not actually a well understood thing, but there are some papers that describe and characterize the brightness of the sky near the moon, or very bright objects like the sun and the moon and so on. So this picture that I took is only because it had a bright, I don't have very many pictures of a bright moon, just overexposed, but this was one of them. Pretend there weren't any clouds here. The question is, as you go and approach the moon, what brightness, if you were to graph it, what does that graph look like? How does the brightness change as you're far from the moon and then you get closer to the moon? That's the night sky brightness that you would want to understand. And it's something that needs to be potentially studied more. So here is one of the papers. It's written by, among others, this Chris Siunis. I don't know how to pronounce his name, but that indicates some of the formula that are required that characterize that sky brightness. And it so happens that this is a piecewise formula in the sense that there is one kind of behavior when you're far from the moon, and then it transitions to a different kind of behavior when you're near the moon. It deals with another characteristic of the atmosphere, which is that when you're far from the moon, there's something called Rayleigh scattering, which is the scattering of light you get that causes the blue sky. And then there's this other effect that's based mostly on aerosols and things that happen when you are looking in a small angle near a very bright light source, and it's called me scattering. And so those two things play off one another, and these formula that you see here, those characterize it. And these formula all together, when you put it all together in one grand thing, you can try to model what the sky brightness is. And so that's what we did. I observed for real the brightness of the moon, the sky near the moon. And then I tried to match what this model, says it should be. And that was the game. What I like, though, is what I've highlighted here. It says these equations are not as formidable as they might look. A pocket calculator can evaluate the brightness of the moon, sky moon, in about a minute, and only a few lines of code are needed in a computer program. Well, I'm hoping that this is astronomer humor, because I guarantee he could not do that. I mean, maybe there are specialists, not today, that can use a calculator that quickly. Maybe back in the day they could. I don't know. No, it needed a little more than a few lines of code. But with those quote unquote few lines of code, this is what it looks like. So here I've taken pictures of the moon, or of the sky near the moon, and then graphed my values that I observe compared to the values as calculated by that equation. And there is a very good match. So he gets good cred, good credentials, good kudos for characterizing with those equations. It seems to be a reasonably good fit. But at some point, it kind of breaks down when you get very close to the moon, within 5 degrees of the moon, then things become very hard to measure. And that is kind of where things are today. If you want to make those measurements very close in, you have to be creative about how you go about doing it. This is just another example of making those measurements near the moon, but looking in using the different filters so that you get a characterization of what it looks like in color far and near the moon. The top graph, though, is an error that I made. It's another one of these examples where you know, in science, you collect data, and that may be hard. Then you analyze the data, which is kind of what graphing and things, you get it, you plot it, and that's another thing. And then there's finally, you got to understand what it's telling you. And just because it's telling you something, it might not be true. So the upper graph, you look at it and you go, well, why is that Z band? It's always, air glow, something. Why is it so far away? Could it be because of that air glow thing? Is that what the atmosphere is doing? Is it something about the system? And the answer is no. The answer is the Z band is hard to take flats for. You have to take very long flats. And I neglected to include them with the other flats that are automatic. And so the Z band data wasn't flatted. And so it looked bizarre. And then when you actually do it right at the bottom, everything makes more sense. And the universe is once again sensible. So just wanted to show it's that's the way these measurements and things go. So that's the science. And I'm going to pause for a moment and take a drink. The other part of this presentation, the part that I hope you've been waiting for anyway, is where I show some of the pretty pictures. So I'd like to go through and show some images that, again, taken with the system. And with an understanding of this other research, now you can understand some of what goes into the creation of these pictures, even as so far as how to deal with the data. But I'll pause for a moment. Simon, are there any questions or something, I don't know, puzzling that people were chatting about? Is there anyone out there? Maybe I should ask that.
Oh, there's plenty out there.
Okay,
that's not even a question. One gentleman did ask about some of the pictures that you were showing with the Orion Nebula. Was how many hours worth of integration time was that?
Okay, well, this might be a good time for me to do the following. If you want to follow some of the work that I do, there are two websites. The first are just the images that I post, and that's at atomblockphotos.com. I've got to kind of show that, right? If we go under Nebula, I always list the, the important information. The thing that makes this a remarkable image is that it's a mosaic of many frames, so it's not a single frame. Each frame, I didn't spend that much time on, but it takes time. So a little less than 3 hours, 150 minutes per frame. And this is only a 2-frame mosaic, actually. So this one didn't take quite as long. I'm going to show you some others that took a little longer. So this one's not bad, and that's because the nebulosity in this region is actually quite bright. But these are 2 frames just placed side by side, and when you show the horizontal view, I like the horizontal view. It's easier to fit on a screen. You kind of get a sense of the relationships, which is what I hope you got when I showed that video in the beginning. The relationships between various objects, like the Horsehead Nebula being near, Alnitak. I can't even remember the names of stars now. And things like that, the Flame Nebula. But over here, you've got the Orion Nebula. Right here is the Keyhole Nebula, NGC 1999, things like that, the Running Man. So the relationship of all of these various things are kind of put in place when you do this wide field imagery, and then you can zoom in with other kinds of images with other telescopes to get yet another kind of perspective.
So real quick, how does SpaceX play into all of this with their microsatellites that are coming out?
So, SpaceX. Are you talking about like Starlink or about just small
Starlink?
Things? Yeah, Starlink. Okay, so, well, one of the things that I hope you got from what I was describing is that it is possible to do some things to mitigate the effect. Obviously, I demonstrated how mathematically you can reject satellites from data. Now, if you're taking your pictures out with your camera, looking at the sky using just a DSLR with a tripod, then you can't reject them. Though, of course, as they are currently low Earth object satellites, they won't be visible for the entire night. They won't be sunlit. But if they do move them out, then they would be sunlit for a greater majority of the night. So there's these things, but this is the state of affairs now with satellites and the era that we live in. I mean, that people are going to be launching satellites up there. So there's going to be, I don't know the answer, but there's going to be a balance between the science and the economy and the service that they provide for us here on the Earth. And that just needs to be managed like anything else.
So one more question before we move on. If we would calibrate an image with a reference star like Vega, is PixInsight photometric calibration a reliable tool, or is there any other free or commercial software that can do that?
So at some point, someone's going to ask a question where if you dig deep enough, you will start hitting the cliche of things that I don't know. And this would be one of those points. So, so in PixInsight, it is possible to effectively measure a flux. So yes, you can get photometry out of PixInsight, though I think there are better tools for doing that. There is one, oh gosh, Photutils. I forget. No, and that's the package. There's a software on my computer that I use to measure little apertures. It's available for free, so there are some free ones. But in general, what's necessary when you're doing photometry is you got to do a lot of sources It's not just one, two, or one or two stars. So to automate that, generally astronomers, it seems as though you end up writing your own little programs to do this, to interact with the data and to make these measurements in some form. So you write scripts and so on. So I don't have a good answer for you. There are certainly tools that astronomers use that do this all the time. In the commercial world, there are some free applications. It's not as common to do because it's more mathematically inclined than it is anything else. So yeah, that's my best answer right now.
Excellent.
Okay.
All right, let's move on.
Okay. So here's an image. It happens to be the first, I was very happy, first color image that I basically took successfully through the astrograph. I decided to take a picture of the North American Nebula, and it was high overhead at the time, and I thought it was, a really nice thing to do, to work on. Something just now, talk more artistic things now, something about this field that I find interesting. A lot of people, when this is just an artistic consideration, they process this field and display it very contrasty, quite dark. Now, all of the images that I'm showing, unlike narrowband images, these are broadband images, lots of light coming through these filters. And in fact, this field is awash with light, mostly starlight. And so you'll notice that I have things quite dark and contrasty where there is that darkness, but not making everything else so dark. I mean, I only use this as my fiducial here, and then everything else is, the corresponding brightness. So this field is actually very, very bright. And so with a large wide field, image, a large image like this, field of view, you really get a sense of that nature of the of this object and this part of the plane of our galaxy. Here's another image, and it's the kind of thing that I think gives a sense of the perspective and scale, especially of using a very fast, low resolution, if you will, system, at least at this plate scale, compared to looking at much more fine plate scales. So can you see the elephant trunk here? And then with the 0.8 meter telescope, I also was fortunate years ago to take a picture of the same. So that thing there is the same as that thing right there. So it really gives you a sense. Here in this image, you can really see that, there's some stars in the middle that are really making the whole thing glow. And then that the elephant nebula is just a small fraction of that entire nebula. And it is just a thicker part of it that is radially being ablated, moving, photodisassociated. It's dissolving away. Gosh, I can't think of the right word. And then, of course, you zoom in and you get a kind of different kind of story when you look at these resolutions. So I did want to try to show you a few more of these pictures, and I'm just going to, because I have the ability to do so, use my webpage to do it. It's just easier. So for example, I had there the Pelican Nebula, which is one of another early pictures that I was fortunate enough to be able to work on. And this is it just worked out really well, a really fine image of this particular region. Let's see, so let's look at the full res here. Even with the small telescope, the details right around here, this is another like little elephant's trunk, but you can even see the little, bipolar outflow right there at the tip, and some interesting structure at these kind of scales of the dark clouds and kind of striated nature of the other bits of the dark nebulosity and so on. So I just thought that this was a really nice kind of representation of this particular piece of sky. Then, as I mentioned earlier, mosaics, of course, become something that is of interest when using an astrograph, because yes, you're taking a picture of a large piece of sky, but there are even larger things at that scale to try to capture. And the region around Antares and Rho Ophiuchi is fabulous. There is probably no better place in the sky for an astrograph to go hang out for a while. And so this gives a sense here of a little bit of what's going on. Here is M4, and I don't remember the number, NGC 6302, something like that. No, not 63, it's 60 something, 63 something. And this object right here is really kind of a cool one. I might show you a high resolution picture of it in a moment. So when you look at something closer to just the full resolution, it's not the full, but it's much more so. You can kind of get a sense of the clouds given their contrast compared to the background. So you get a sense of that depth where these clouds are in the foreground of everything else that you're seeing here. And this happens to be relatively close to us compared to these other features that we're seeing well beyond, like M4, for example. Now, I believe that I have, with the system, I took a picture of the Andromeda galaxy, very similar to the one that I showed before that had the moon, but this time a little different. I handled the data a little bit differently here, in that I did spend a fairly good bit of time to capture this information. And what I discovered is that, you know, when you go relatively deep with an astrograph, you really get a good sense of the contrast between the color of the sky and the objects of interest. And the galaxy has kind of a halo of glow around it. And that halo is white to, you know, I wouldn't call it yellow, but it's almost a yellow, a little bit of a white yellow kind of color. And so I left that here, not having the galaxy look like somehow I could increase the contrast in blue and give it that kind of blue, you know, encircling spiral structure. It really does not come out like that. Instead, there are blue highlights of the stellar associations along and within the spiral arms within the disk. But overall, it has kind of this white, yellow, white glow. And then, of course, reaching inwards, spiraling in with all the interesting structure and detail that, you know, doesn't come across that much here in the astrograph, but with high resolutions, you can see. One of the effects that I'd like to show, given some time here, is what makes an image like this possible is compressing the dynamic range, because this, when you take this picture with the astrograph, the galaxy is overwhelmingly bright. So you have to compress the dynamic range in order to be able to show these features of the spiral arms and the dust lanes that are going within at longer focal lengths. That isn't as much of an issue. So I'd like to demonstrate one of the processing things that is often done to compress the dynamic range and allow for this kind of imagery. And let's see, something that's a little more topical, more recently, let's go up above then. Solar system. Oh, that's the, I was going to do this one first. So this is Pan-STARRS. This was in the sky not too long ago, a month plus ago, and it was passing the double cluster, which is just really pretty, of course, to see a comet and the double cluster together. Anytime you get that kind of pairing, and that those kinds of things happen more frequently, the larger your field of view. So the astrograph, of course, played an important role in being able to do something like this relatively well. And then most currently, of course, this is what on the 29th Atlas looked like. I decided just to go ahead because I liked it so much to show the starless version of the comet. And then, of course, you eventually blend it in with the stars. So this, you remember the rejection technique that I showed for satellites? It's the same idea here, where you have the comet moving against the background stars. So if you align on the comet and you combine the data as I showed, like for the satellites, all the stars will get rejected, and then you end up with only a comet image. And you can try to do the same thing to reject the comet and only end up with stars. And then you take the two images and put it together, which is the bottom image. But that is an option that is available in PixInsight. There's a nice process called comet alignment, which allows you to do this. And that's what I use to create this picture. I don't want to show you all of the images. I'm just going to do two more here really quickly. There are lots of cool things, but I'm trying to stick to just the astrograph stuff. Since I mentioned it though, there was that blue region. I think I have a picture of it. Oh yeah, this one. Remember the little blue region that was in the row of fucus area? This is what it looks like if you look at it with a higher resolution. Oh, yeah, the page isn't there anymore, I know. Okay, anyway, that's what it looks like, higher resolution. And then finally, a question, but it has its own answer. This was also a quick kind of 2-frame mosaic, which is a cool nebula. I don't see it until there it is. Yeah. It does look kind of like a question mark, I think. But this is the region near NGC 7822. And you can see at the highest resolution, you can actually see some of the detail. Let's see, here's the larger version. You can see some of the detail in here, but of course with this astrograph, you really can't get, what you can get if you zoom in and you see all the other features that are really prominent, especially narrowband imagery when you look at the center of this object. But just having that little strongum sphere down here at the bottom really does add a punctuation literally to this image. So let me go back and show you a few of these vignettes that I mentioned. Let me just be sure that I'm getting my slides here before I forget things. Vignettes. Yeah. So not so much a demonstration. This one I'll just show as an example, but I wanted to mention something that's interesting for undersampled imagery, which is what you're doing, taking pictures with an astrograph like this. The stars are literally little squares, little pixels, because they fill only a single pixel. Consider that these are 5 arcsecond pixels, and the seeing might be less than 2 arcseconds easily. So the stars fit inside the pixels. Well, the same thing kind of happens if you're in space and you have a space telescope, because the diffraction limit of your telescope might allow you to create stars that are smaller than the pixels of your camera. And that is exactly what happens with HST imagery. So there was a nice algorithm developed called Drizzle, which attempts to compensate for that effect, the sampling problem of that effect. So the way this works is, and this is actually taken from the manual of Drizzle, that is, if you look up HST manual stuff, you'll find this information in there. But at the top left, you have the picture that is basically the perfect picture. If pretend there was this big, I don't know, sign out there of letters way out there, light years away, and you had your infinitely sized telescope with infinite resolution and so on, you could get infinite detail in your image. So it's perfect. It's a perfectly formed image. Now that isn't actually what you end up getting. What you actually get with even the Hubble Space Telescope, now this is disregarding the sampling problem. Pretend you had a infinitesimally sized pixels for your detector. So the detector has nothing to do with the output image. You have a perfect detector, but you still get a little bit of a fuzz here because that's just the nature, the diffraction limit of the telescope. So that's the best you can do in terms of forming an image. It's the quality of your optics. But what you actually get with HST is the combination of that diffraction limited image plus the sampling of your detector. So you get an image that looks like this, and that's exactly what we get when we use our astrograph. You get these little undersampled images. So to correct for that, you use an algorithm that's called Drizzle, and you try to compensate for that effect. It's kind of a cool idea. The idea is that you have your data, and what you're going to do with your image is you're going to create a finer scale to operate on, or to operate with, I should say. So here is the original image. Notice the grid here is larger than on the right, where the squares are literally smaller, in this case, half the size. So often Drizzle is done in increments that are like you double or triple or so on the image. So this would be a doubling. So when you have more pixels, it means you literally have a larger image as well. You literally have more pixels there. And what happens is you have a reference image which you have resampled with many more little pixels. Now that doesn't change the reference image in any way. But when you align all your other images to this reference, you do this cool trick. So that's what this is showing here, this alignment. You transform one of your images, into your, you transform it into your reference image. And what'll happen is you need to do something. You're going to need to manipulate one image to make it match another, just as we normally do. But instead of using an interpolation algorithm, instead of trying to decide, you can see that one of these pixels here in the original image now falls on different pixels in the new resampled image. You have to decide, well, how much of this information do I put in this pixel or that pixel or this pixel and so on. In the normal way you do it, you look at all the neighboring pixels and you find some interpolation method where you measure the values between pixels, and then you pick an output value. And there are many different interpolation methods, but Drizzle works differently. Drizzle literally says, pretend this is like drizzling, like a drizzle of rain, like little drops of water. If you were to drip a little bit of water, pretend one of these boxes was a drop of water, well, what you end up doing is you put this quantity's worth of the water in that pixel. There's no interpolation. And then you put the some quantities worth in this pixel, this pixel, this pixel. So this pixel here only has a tiny little bit, some little number amount. But you don't, this is not going to work if you only have one image, right? You don't drizzle between two images, a reference in one. You need to do a lot of images. And in that way, you end up through all of these other subsequent images, you're going to be drizzling more and more values in here. They won't always land on the same little squares. And then you will fill the information there. And the byproduct of doing it is that you're taking advantage of the extra dimension of these squares. Because you'll notice that I'm able to reach here, this square, into other pixels because the diagonal is longer than one of the sides. So you get a little bit of extra spatial information there. And that helps basically round everything out from the undersampled images that we were seeing before. So on the left is an example of the bubble nebula from data that was courteously given to me. And this is what it looks like if you just do the regular method of processing the image. You get that undersampled look with blocky little stars. Now, it's a very subtle effect, but on the right, you get the result. Now, I've zoomed in. I don't know if you see, that's 300%. So when you're at 100%, it's a very subtle effect, but you kind of correct for that sampling error. And you do it in a way that is very different than if you were to do the same, I didn't show this, but if you were to do the same thing with one of the interpolation methods, you would find that the images would be much, much blurrier to the same degree, especially if you display them at the same scale. So Drizzle is a wonderful way to retain that spatial information and get rid of some of the sampling errors there. That happens to be the final result of zooming in on this thing. I don't actually have a final image of that particular data, but this is an image taken through a big telescope, but that's another story. Okay, so Simon, according to what I see, I still have maybe, if I took another 15 minutes, that would be okay. Does that sound okay?
Oh yeah, plenty of time.
Right.
I do have two questions if you have time for that.
I'll pause, yeah.
Somebody's asking, is it better to be undersampled or oversampled if you had to pick?
So I would pick always being a little bit oversampled. There are a number of reasons for that. One is that there is really no downside other than if you're super, super oversampled, you're smearing the light out. And so then you have a degradation of signal to noise versus the amount of time that you're willing to spend to get a particular level of signal to noise. But the fundamental answer is that there is really no other bad thing that happens by oversampling. When you're undersampled, lots of weird bad things happen. This is one example. Let me just give you another one. When you are processing data, if you want to use a hot pixel rejection to reject hot pixels of your data, well, guess what looks like little pixels? All of the stars. It's harder to use a hot pixel filter, whereas if you're slightly oversampled, it's much easier because the hot pixels don't look like stars. And so, for example, you have to be sure that when you're using, like this telescope, undersampled data, that you dither the data in order to correctly identify things that are the same instrumentally, systematically the same from image to image, because everything looks like little pixels. So given the opportunity, you want to be slightly oversampled. There is actually some criteria that's the optimum, but slightly oversampled if you have the ability to do so. When I was using the big, the 0.8 meter telescope, that's imaging at 0.33 arc seconds per pixel. That means that on average, my stars are 4 to 5 pixels in size compared to 1. So, that's really oversampled.
So next question is, what do you consider as a critical step? Is it the acquisition or the processing?
Oh, well, so in terms of acquisition, this is a GIGO thing, garbage in, garbage out. There is no way around it. So acquisition is something that it needs to be done right. It's not that it's more important, but it needs to be done right. The processing, though, is really what makes the image, given what you're starting with, whatever it is that you want, whatever goal that you have. Now, for me, my goal is public outreach. My goal is to captivate. My goal is to some way communicate through the imagery. So I have goals. And so the processing to me really suits my end goal. For some people, that's not as critical. I mean, they just want to in some way see something, and that's good enough. And for me, there's an nth degree. So if I give you the data that I took through the same telescope with all that carefully done right acquisition, you're going to come up with a different result from the data. And that has to do with, I'm not even talking about skill here. It also deals with an artistic rendering and interpretation and communication of the image. And that, to me, is certainly very powerful. And so that's why I would say processing might have the upper hand on acquisition. I mean, once you've done enough acquisition, a lot of people like to fiddle. I really want to get the raw data so that I can start working on it.
Excellent. All right, let's move on.
Okay. So what I was going to demonstrate is something that's very important for wide field imagery, which is, and this might not be the correct one. Let's see. Well, that might not be true. I want to show the correction of the background due to either, could be either. No, it's not that one. Sorry, guys. Flat field errors or other sources, instrumental problems, optical problems. Yes, this is what I needed. Okay, so let me close that, this, and open this. Now, some of you that might follow me may have seen this before. This is a pretty standard example of this, but I just got to show it because I think it's just a really remarkable example. Recently, I've had the opportunity to work on the Pleiades. Wonderful thing in the sky. Of course, this is topical for tonight, especially if you have clear skies. You should probably go out this evening and see the Pleiades, because unlike this picture, there is going to be a very bright thing there, which is Venus. Will be right in front of the sisters there. So they will have some bling, to say the least. So here we are with the Pleiades, and let me be sure. Yes. If I zoom out, I'm hoping what is obvious here, and I might be able to make it yet more obvious if I get out my screen transfer function. Zoom in. Can you see that the outer part of this image looks like it has this brightness?
Yes, we can totally see it.
That is not a flat field error. This has something to do with the fact, I think, I haven't really run it down yet, but whenever I have really bright stars in the field, there is probably an internal reflection. I don't know if it is at the flattener or maybe the inner tube or what surface is in there, but they are circularly basically scattering light. And it acts as if it is vignetted in the opposite sense, right? You have brightness to the edge instead of darkness, which is crazy. And one of the things that people typically do with DBE and by the way, for those that are not familiar, this is PixInsight. I've already assumed that you know what this is. The processing software And there is a function, a process that is called dynamic background extraction. And it will allow you to try to model all of this information and then compensate for it. So that's the idea here. And what typically happens, let me just remove this because I should have let me think, there they are. I have a typical example where you've placed in this image, as many points as you can scattered around the image, trying to avoid the nebula, but you want to just blast the image with samples everywhere and then hope and pray that when you press this button, it somehow magically compensates for it all. I think that's hard. It's more likely to make an error, and you might not see, the nebulosity where it is, and the corrections could be a little flaky and so on. So let me just go ahead and demonstrate that the result that you get is not necessarily, I can see stuff, but there's an error down here at the bottom somewhere, and there's kind of just this haze there, but the contrast of the nebulosity, I have no assurance that I've really done a very good job at the end of the day. So I want a better way to do this so I can really tell that I'm getting rid of what is apparently a fairly symmetric and global problem, which is this glow. And then if I still need to make another adjustment of things that are left over, it's much easier to do. And so that's what I was going to demonstrate here. What you can do is take advantage of another property of dynamic background extraction, which is that you can place samples like, and let me just set this up. So I don't know, I'm going to do 5 for the tolerance, and I'll keep it really smooth, 0.6. We will make our little samples, I don't know, 18, doesn't matter. And that's it.
So I'm going to place this. It didn't change. Your smooth factor is still at 0.25.
Oh, it won't matter, but thank you. 0.6. There we go. Thank you, Simon. So you click here on the screen, and what I notice is that in this part of the image, I can see nebulosities here. It just so happens right around here, there just doesn't seem to be that much. So I can safely just kind of click over here, and I kind of move this around so I get a space that doesn't have too many stars and things. And what I do is I claim that this point we're going to have to have some kind of circular symmetry like this. So I make it like a circle. Maybe I make it a little more out here, right? And then place another point, trying to avoid nebulosity or whatever. And then, because I need to work inward, this is obviously radial. It's a radial thing. So I go like that. And then maybe some final point, and I'm not paying attention. If I were zoomed in and messing around with the brightnesses and so on, I'd probably get a better answer. In fact, I have one there in the oven as it is, so I might show that to you. But anyway, go like this, and then we make it a circle. And then we say, okay, let's see what happens. Yeah, we do that. Oh, I haven't done yet. So the correction method is division, and that's it. So this is what the model looks like. That looks pretty good to me. I think that that'll probably be a good fit for compensating for what we're seeing here. So we go, okay, and now let's actually do it for real. Oh, well, that's much better. Now I can start to see some of the stuff that is going on in this field. And all I had to do was do 3 points, 3 points. Did a majority of the work here. Now I do notice that these corners, especially the top left and the bottom right, they still need some work. Now I will not spend the time here to do it, but what I should do is you will close this like this, and then you would open this and do one more iteration here. And see, I have to set it up again though. So I might still do, I don't know, 3 or 5 or something, maybe 3.6. And you make a sample there. You make the typical sample. I'm not really doing this with much care or caution. Do I have samples? Okay, I do have a sample. Good. Make samples. I'm making a sample here, here. Can you see how careful I am being? Right? So I was not very careful about this at all, okay? And if it doesn't work, I'll show you the one that's in the oven. But what have I forgotten? I don't know. Let's do it. Yeah. And it pretty much corrects the field. In fact, I will show you the one that was in the oven just so you can see it. But now I can really see the nebulosity and raise the contrast. And the point was, and I didn't make this earlier, I'm sorry, this is the red data. If I can see some of this outer nebulosity in red, then I really am doing a fine job here, because it's even easier to do this in the other colors. The red is the one where the signal is very faint. So having made that correction then, and then you combine the data to make a full color image, it results in a couple of things. First is that you can take the color image. Well, I just show you the final result here first. Here's the final result. Without making that correction, using DBE in the way that I did it, I don't believe it would have been possible for me to display all of these wonderful differences in the nebulosity that is surrounding this field. I was really striving to display the Pleiades in a way that I didn't think had been done in the same way before. I'm a big proponent of light. I like light. A lot of people like darkness. I like light. And so I just felt that displaying all of that stuff here, even at the expense of some contrast, was something that was powerful. And one of the things that I love that would not have otherwise come out very well is that there are bits of maybe blue reflection stuff, and then behind them, there are these dust clouds. So it gives this three-dimensional feel to the image as well. So all of that only came about because of that use of DBE. And in particular, one of the side products is that I did take advantage of a starless version of this image to enhance some of that nebulosity. And again, I would not have been able to generate this starless image without that very fine, high quality DBE compensation. So I wanted to illustrate that for everyone. The other one that I wanted to illustrate is also very important. Okay, sorry, I'm making sure that no one is email or texting me right now, which is the use of that compensation of the dynamic, of the compensation, I should say, the compression of the dynamic range of an image. And in this sense, there are many objects that are very bright, and this happens often. It did with, for example, the Orion Nebula, the Andromeda Galaxy, many other bright things up there require this kind of treatment. And the way in which it's done is quite interesting in PixInsight. So there is a process that is called HDRMT, which is high dynamic range multi-scale transformation stuff, has a big name, but it does some pretty remarkable things. Let me first show you an image of, this is still in its linear state here, but it's an image of the Lagoon Nebula I took some time ago. Now, this was taken through the 0.8 meter telescope, but I want to show this for a different reason. So you can see here is the lagoon. And what you end up doing in order to take advantage of this compression is you actually display the image brighter than you otherwise would have normally done. Because what we really want here is we want to be able to see dim things, and then things that are overly bright, we can batten them down a little. We can, prevent them from being too bright with the application of HDRMT. So I'm just going to choose some level here. This is not necessarily the best level or the worst level, but there it is. And then I am going to permanently, there it is, permanently stretch the image like so. Did I get it? And then finally, you would apply something like HDRMT, which I will go get. So I'm just going to randomly pick something that I think is going to work. It's another lesson to appreciate why I'm choosing what I am choosing here. But you choose some values that are hopefully going to knock down on the brightness here and allow you to see that structure, but still also allow you to see all the cool stuff that's going on. So I'm going to apply it. This takes a moment. There you go. And what you end up with is an image that really goes a much, it takes you further along the path to being able to create a beautiful color picture. One of the byproducts of HDRMT is that you gray the image a little bit, and making an image gray can be very powerful, especially if you're going to be blending color with it. When the image is very bright, it's very difficult to colorize the image, especially when doing LRGB imagery, and that's what I was doing in this particular case. But I used HDRMT, I used this process here on the entire image. That is not typically how it works, because the calculation of these brightness levels that you're choosing to compress is done across the entire image that you're working on. And so if you have a small object in a large field of view, such as this, the calculation that you get isn't going to be representative of what you need for just the object. It's only going to apply to the entire field, which may or may not be useful. So what you end up doing is choosing a preview and working on the object, but only around this region, and then basically writing that information back into the image. And I'm going to show that to you. But first, let me show you the end. Yeah, I'll show you the end result of the lagoon. So with the application of HDRMT, now you can really start to see all of these wonderful structures here, all the way into the center, as well as, you know, to the outskirts and all the dim stuff. This is the very nearly the full resolution here. So wonderful things going on within the nebula. Now that, of course, this is what you get with a 0.8 meter telescope. Keep in mind, this is not narrowband imagery. This is just RGB. This is broadband imagery. And I can get this level of contrast mostly because of this dynamic compression of the dynamic range in the image. Okay. So back to this one. This is a galaxy which obviously needs, there is no way to linearly display this galaxy. If I choose, let's be sure that I'm doing this here. Is this already a stretched? This might already be a stretched image. Let me see. I can't remember if this is a stretched image. Yes, so this is a stretched image. So what I was going to demonstrate is there is no way in the linear space that I could somehow display this image and show both what's going on inside and what's going on with all the faint outer structure. This galaxy must have been perturbed at some point in its life. It has all kinds of crazy shells and tidal things going on here. Inside, though, it's very difficult to see, but it has this wonderful edge-on galaxy. It is an edge-on galaxy with this outer halo that's just bizarre. This obviously requires HDRMT, so we will get out HDRMT again. And I'm going to apply it, but only apply it here to this image. Now, the number of layers deals with the scale and size of things that I want to operate on. I had a moment ago something like 7 when I was operating in such a way that I was interested in the large scale structure of the lagoon. Here we can make this perhaps a little smaller in both of these scales. And Gaussian is fine, that's fine. So this should do a reasonable job, and maybe I should leave it at 7 here, I don't know. I can't remember what I actually chose. Yeah, that's probably better. Okay, so this might be something closer to what I'm looking for. Now you can really see this wonderful edge-on galaxy in here, as well as the outer structure. But the good news about HDRMT is that one of the things you'll notice is that, let me undo and redo. Can I? Yeah. Notice how the background brightness remains the same here. It does a wonderful job of still maintaining the same sky brightness. That's going to allow me to do the substitution of this image here in just a moment. But the wonder that it does on the galaxy, it does a little harm to the stars. You'll notice that stars get a little bigger and fatter. You go on and off here. It's hard to see that. They get a little bit bigger and fatter in the process of applying this. And of course, the very brightest stars here develop something that's kind of like a ringing effect. You get kind of a darkness surrounding them, you get kind of a weird thing going on in the center there. All of those things we don't really want. So I'm not going to construct it, I'm just going to pull it out here, which is that such a thing you can make is a mask that looks like this. And this mask would do the job of taking care of the stars that are within this image, so that the stars are not a problem because you protect them from the effects of HDR-MT. So let me show you how it all works. What you do is I make an image here of that preview exactly how I want it, except that I need it to be in the state before the adjustment, sorry. Let's undo that. There. So there's the preview. And I know that I've done it around the object, so I know HDR-MT is going to get the right kind of values for the brightness and do its job. Then we can apply here my mask. We do, I'll turn off the showing of it. We do the job, which is here. Now you'll see that I've mitigated the effect of showing the badness that happened around the stars. They don't look weird in the center. They don't have much of a halo ringing effect going on. I see what I see and so on. And then the final thing that I do is I need to put this thing back into here. So there are a couple of ways of doing it. There is a substitute by preview. There is a way to do that with a thing, but it's overly complicated. So I made my own little script which does that, and I should have it right, not script, I should call it an expression. You just put it into pixel math, and I'm trying to get to it here. So all of this, by the way, this kind of stuff is available. I believe I have this open to everyone on my website, which I'll show you in a moment as a last thing. So does anyone see insert? Here it is. So all I need to do are find these values here, which I actually need to write down right now. So the values are, so I have 1335, 1542, 1527, and 1167. So all I'm going to do is just put that into my expression. To the bigger image. That's all this thing is going to do. 42, 1527, and 11. I know you guys remembered it. 1167. All right. Okay. Oh, I got to do one more thing. Got to change the name here. In fact, I'm going to change the name of this thing to make it easier to type. Not that thing. Sorry. Where's my little, this thing? This thing should be HDR-MT. All right. That is not the one I dragged, though. There's my mask. That's the one I want. Okay. Sorry, I have too many of these things. HDR-MT1. There we go. Because I had some pre-made. HDR-MT1. I believe that should work, but let's see. Ta-da! And I will remove the preview. And now you see in place, in situ, if you will, I have put this modified version into there. I had the mask on and everything. There's actually another way to blend it, but in this case, it didn't matter. There is no demarcation. There's no way to tell that I've done that neat trick. Now there is no reason why I couldn't have done HDRMT to the whole field and then masked the stars, and then really all I'm operating is on the sky, but that's just silly. That's dumb. There is no difference between me doing this as a substitution and me doing this globally and masking everything. So I just make a small image and substitute it back in, and I have more control. It's easier for me to work with that small image than it is for me to work with the entire image sometimes for masking and other reasons. So there you have it, another very powerful processing tool or technique that often comes into play when doing wide field, doing imagery in general, but especially doing some of the wide field imagery. So the final result of that image is this guy. Here is what that galaxy looks like after that treatment. And what's nice, of course, is that when you're able to display the innards of this thing, it has these wonderful little bluish bits at the end, which are probably, again, the spiral, it's probably a spiral galaxy. And you can see the dust lanes in here, maybe a little stuff, as well as the outer structure of the galaxy. So if any of this kind of information interests you, I would highly encourage you to go to another website of mine, which is called atomblockstudios.com. And it is here that I offer all kinds of content on processing astronomical images. I have lessons, most especially these days, it's all on PixInsight, but I also have the other information here as well. There's a fundamentals where people can purchase for one-time purchase. You get access forever to the entire content of the entire archive and content of that stuff. And there are, how many hours? I don't even know how many hours. Most people, it takes months for them to go through all of the videos that I've put together just in fundamentals. And by the way, if anyone is interested, it is fundamentals that you want to start. And then I have a growing collection of things here in my other section, which is called PixInsight Horizons. It's here that I have lessons on how to process individual data sets where you get the data so you can follow along with me. In addition to that, I also have other lessons that are on different techniques, some of which are innovations that I've developed all on my own, like star de-emphasis and things like that. So you'll only find them here, right? I gotta sell it. So there you have it. And on a last note, if anyone's interested, because of what is going on in the world today, it's harder to go out and do things. So I am now offering office hours with Adam. If you would like to reserve some time you have just some problem, you can't figure it out, and you go to a forum and you really just need to be shown, you need to work with your data. It's either the hard part is work with your data and your PixInsight, make it work. That's what I can potentially do, because you can go join me and online we can work. I can work on your machine, try to solve a problem. And I have some experience doing that. We're doing workshops. So it's something that comes naturally to me. And if there's any interest, you can email me for more information. And with that, I promise to be wrapping up at 4, right? So it is 3:55. So
3:55. I mean, we're going to cut this one. Well, I mean, if you're pretty much done, don't forget we've got one more video we've got to play. And then we're probably going to take a break for around about 20 minutes. So we're going to delay Chris Go for about 20 minutes.
Okay, that last video, you can play my video, but if there are any questions, I'll ask them or answer them. That last video is not necessary. It's just a nicety. I didn't really need it at this point, but it's cool if you want to
we'll play it for these guys. Okay. I think everybody's just like their jaws have just dropped and hit the ground, to be totally honest.
Okay. Well, this was a talk that was not prepared, right? Because I was only told last Friday or something. So this was extemporaneous. This is what it sounds like when I do things on the fly.
But you know what? In all honesty, and I say this on behalf of everybody from Woodland Hills Camera and Telescope and here on the chat, I think we've probably learned more in the last 2 hours watching this than we probably have done with anything else that we've ever done. I mean, I've never seen the Pleiades cluster look like that, ever.
Yeah.
And I've imaged that thing countless times. I've not gotten anything as close as that. It's just mind-boggling, absolutely mind-boggling.
Yeah, the wide field helps, and then the combination of some of these techniques of working with the data obviously can give you that kind of result. And when employed for that purpose, it can be powerful. Yeah.
Definitely. I think, I mean, you guys who are watching at home right now, I really do highly recommend that you check out Adam's website if you haven't already. And if, like you said, if you get stuck, take advantage of these office hours. I mean, that's what it's for. I mean, yeah, I do have a cat, just so you know, that you can hear her going nuts. She just wants attention now.
Mine left the room about an hour ago, so.
So yeah, we're gonna open it up for like last minute questions. We'll try and take one or two, and then we're gonna go on a 20-minute break roughly before we bring on Christopher Go. I gotta eat something. I've been sitting here for the last 3-4 hours and I haven't really moved, and I need to go to the bathroom and all sorts.
Well, I'll take a couple of questions, and if you wouldn't mind, just as a fade out, playing that last video.
Of course.
It's another nice one to show the wide field work with zooming into some of the high res stuff.
So one of the questions is, how do you compare HDRT to LHE? Obviously, this is in PixInsight.
Yes, this is. So LHE, I think of, it's local histogram equalization, I think. I think of that like an effect which is similar to, if you worked in the Photoshop world, it's almost like soft light blending mode, where you really make things, you make things that are dark much darker, so it really increases the contrast, and things that are bright kind of get brighter. Where HDRMT does not give you more contrast. In fact, it probably does the opposite. It gives you less contrast, but it allows you to see more brightness levels simultaneously. So they're really two different ways of interacting with the data, and they give you two different outcomes.
Next question is, what is your thoughts on binning? Just by the way, I have a problem with that word sometimes because I pronounce it as bining.
Yeah, no, sorry. Because you put it in a bin, not a bine. It's binning. It's literally going in a bin. Okay, anyway. So my thoughts about binning are, I am someone that has worked with binning data because I've used oversampled data, especially when I've been using a large telescope. I do that because there is a benefit, a time savings. Now, this is an argument, and there's a big argument, and I'm not going to go into it. But there is a time savings. You do potentially, not in all cameras, not all the time, but you can potentially get a better signal to noise result because you are doing better against the read noise when you bin. You get a better signal to noise when you bin compared to the read noise because you're only reading once per that pixel, which is now a super pixel. And the benefit of that is that if that is true, I can save time when I collect my color data and just use more time for the luminance to match those signals, so I'm coloring everything I'm getting in my luminance image. This was very important to me when I was running programs, and I had people come to the telescope and they wanted to collect data, and I spent the night with them. Well, we only have a limited amount of time, so I need to get as much of that data as I can and give it to them, and binning the color helped. Now, with the astrograph, no binning. There's no benefit to binning. In fact, you hurt yourself with binning. So all of that data, of course, is taken unbinned, just straight up RGB, no binning at all. No benefit to binning. In fact, even with the big telescope, if I had a very bright object, there's no benefit to binning. It's really about faint objects and beating the read noise. If that's a true statement, it can help.
Okay, last question. What was the focal length that you used to do the Pleiades shot?
So that was with the astrograph, and its focal length is 500 millimeters. It's an whatever, 2.8?
Yeah, which astrograph were you referring to? The Epsilon, right?
This is the Pomenis, the one that I've been showing the pictures, yeah.
Yeah, so if you guys are obviously interested, we sell the Epsilon. I've been twitching to get a hold of one of these for a very, very long time. We do actually currently have 1 or 2 in stock at the store. So if you're trying to recreate something similar to what Adam has obviously done with, varying levels of success, of course, then you guys are more than welcome to have a poke around on our website and check out what is going on. I believe there are some specials. I think there are people still ready to take your phone calls and things like that. So check out our website, telescopes.net. Otherwise, you can give us a call on 888-427-8766. And this is my cat. She kind of looks like a black hole because she's a black cat, so all the light just gets absorbed by her, so you can't really see her very well.
Is her
So
name
on that
Vanta?
note, thank you very much, Adam.
Okay, thank you.
And hopefully we'll see you again soon.
All right, so play the outro, and thank you guys very much for joining me this afternoon. I had a great time.
Thank you.
Part of the challenge that the amateur astronomy community is facing is to bring in more people into the hobby. So we been actively trying to contact different people, science communicators, people with influence are also interested in astronomy, to help them help us popularize the hobby. I think it's very, very important for all of us to do that because as a hobby, we want to make sure that it's growing. And one way to do it is reach out to younger people, make sure that the next generation, the younger people, are actually getting into the hobby.
Basically, I look at it now and I think of astronomy as more of a really artistic. You look at all the beautiful pictures that they do, and I think that's going to bring more people in. It's like getting the big buck for the hunters. You want to get the most beautiful picture that you can get, and it's kind of a competition, really. Something that can be achieved, and you don't have to have physical strength. You don't have to have all these different things, but you can go in and just be able to have that creative spark and eye, and go out there and work with it.
I guess what I do is I have a small group of friends near my home. And if I have a night where I decide to take out the telescope, I'll invite them along. It's not really their hobby, but it's nice to branch that out. But I would like to do some outreach to some high schools or elementary and get the kids interested early so that it's not something you're starting when you're 20s or 30s. It's something you start early on and you just get that for your whole life.
Already we can see that the impact of social media has popularized astronomy a great deal amongst people who just have no real direct interest in astronomy, but they get excited about these things, like this eclipse that just occurred. Had one of the largest turnouts that have ever occurred for a solar eclipse. And I think it's 100% due to social media and the news coverage that it gets. So I think that is making it more important. In other words, you can reach people much easier now than you ever could before.
I think the general public is more into, the now results, So a lot of people like to share things. I find that people like sharing, they want to see results, they want to make things easy. So I see a expansion into just easy imaging and sharing.
There's a lot of people now doing science, not just astrophotography anymore. There's a lot of people doing science. There's a lot of citizen science, and there's schools that are doing science. The easier we make the telescopes, the more science that the schools can start doing. We get colleges doing science, and maybe even down to high schools doing some science projects with NFS grants and such. So because the capabilities of the telescopes today are so much more, I think the way to get the young people involved is to get them using them in schools.
On the scientific point of view, astronomy is trying to answer very fundamental questions, and most of them have to do with cosmology, meaning where does the universe come from? And there are still many questions. Most of them are unanswered. The other search, I think, in astronomy is searching for other planets, other intelligent civilizations, or even sign of life, simply sign of life on other planets. I think that's the second quest. The first, I believe, should be trying to find out, answering the big question of cosmology today.
I think there's a renewed interest in astronomy. It really peaked for our generation, or the generation slightly before us, with the moon landing and the Apollo program. And then we had the space shuttle, but with the cessation of flying the space shuttle, people predicted that there would be less interest in astronomy. But as Cassini and some of the other probes have demonstrated, a lot of interest is generated because we're getting looks at our solar system with the technology that has been put into these probes that we were never able to get before. And I know that the generation, my children's generation, has a lot of interest in these types of things, and I think that interest will continue. And those are the future astronomers and future amateur astronomers that are coming out of that.
I think what you're going to see, and what you're already seeing, is that amateur astronomy is making significant strides in the professional realm. You've got amateur astronomers finding comets and asteroids and near-Earth objects, and I think that's just going to continue to happen. I see a network of astronomers, maybe a network of satellite imagers. If you can turn households into a satellite spot, and suddenly you've got a satellite telescope that's the size of a hemisphere, you know, just because amateur astronomers are working together. I see that happening. I see the entire community coming together and doing more.
In terms of making astronomy something that it can reach a much broader audience, we want to see more development of those accessibility options via the internet and ease of use, to try to make it a simple process. Using your iPhone is a pretty easy thing to do. And it'd be great if we can get to where people can access these high-end telescopes and take these terrific images and also do research. You think about the science projects we did when we were young, in some respects pretty primitive what kids can do today.
One of the most successful programs that I've seen for engaging younger students and younger kids in astronomy is the Sonoma County Astronomical Society has a program where they have students, little kids, like write essays, and then they take the best essays on astronomy and they give them telescopes. And these kids, I've been surprised, it's mostly girls. These kids, they get these telescopes, they bring them to star parties, and they become little experts, little amateur astronomy experts, and they give public talks and presentations, and this is one of the most successful places. I'm a member of about 5 different astronomy clubs, and this is a great way to bring in a younger generation and help them maintain it, because we've seen over years now these kids come in and they stay in there, and this is a kind of program I think we need to scale it, we need to use it as an example and do it elsewhere. Just sort of one small example of one thing we can do.
We live in a fast age, right, where our movies and our music, our media, fast edits, instant gratification, loud and in-your-face kind of stuff is required to hold people's attention today for a half a second, which is sad. And so the subtle and the esoteric stuff suffers. I think it's very difficult to get a lot of younger people into this as a hobby. It seems like there's more younger folks, even women, who manage to get into the professional sciences, astronomy, cosmology, whatever it is, but in the amateur way, getting them to a telescope, getting them to a dark sky, inspiring that wonder in them, it's difficult, I think.
Giving someone the opportunity to not only see it for themselves, but do it for themselves, and say, here, have a look. If, for example, if they have the privilege of looking through a telescope and seeing the rings of Saturn, give someone that opportunity to do that and see it for themselves with their own eye. It has an incredibly powerful impact. And what I'll find, and for those who, like I say, there are many outlets where you have an opportunity, city star parties, outreach events. Once you see it for yourself, it's like a catalyst that the rest starts to take care of itself. The interest will be there.
One of the things that concerns me greatly is the fact that so many people are moving away from science and from facts. The fact of the matter is math, history, science, and facts matter. And so to advocate that and to advocate education, I believe that college education should be absolutely free. We should be investing in the brain trust of this country. And so to me, our job is to advocate science. Our job is to inspire people to really embrace what is right.
The stars are for everybody. And I would like, if I could do that, if I could spread the interest out amongst everybody, that would be the biggest contribution I can make.
I'm Jen Winter, and I own Daystar Filters, and we're actually out of Warrensburg, Missouri. I've had a very strong math background, and I was studying mechanical engineering very early on. When I was in school, we had a gentleman who was working in Kansas State University, and so he went around to every school, everywhere, brought every student, every person in town went to the planetarium that year. And in my little group, as we were going up to the top floor, we passed a room in this physics building, and here were these guys in their little brown corduroy suits, just all excited because Voyager was going by Saturn, Jupiter, I don't even remember because I was so small. But here they are, they're showing video of a planetary pass and getting data live. They were coming out of their skins, jumping up and down in the chair, and I'm like, well, you know, this is really interesting. And I was fascinated at that moment, but I got dragged away to go to see the planetarium, which frankly, after seeing actual images of the planets, seeing the dots was a little bit less.
Well, I started astronomy in 1976. By 78, I was building my own equipment. Joined the Los Angeles Astronomical Society in 76 also. By about 1984, I had a cave Astrola mount that I had modified extensively. And one of the gentlemen from the club said, "Why don't you build your own mount? You have enough equipment to do it." And I said, that's a good idea. So that's when the GM100 came out in 1986. Then in 1992, we started making them for a major company. Did that for 5 years until 97. And in 97, we broke apart from them and started making them on our own and selling them. Well, at the time we built the mount, which was a GM100, which looks very much like the G11. There was no equatorial mounts really out there. You had, a couple from Japan, I think, but most of it was all fork mounts and no equatorials were out there. And so we started doing that and just happened to come out with a very good design that was, really has not changed much over the 30 years it's been out. I was always trained by my father when he says, when you build something, just add extra holes so that you always have something to come back with to bolt on, and that's what I always did. So we always have holes there. People go, "What are these for?" And I go, "Don't know yet." So it's a good thing to have, and it's always worked out well. So I think what we're trying to do with our mounts is give
how are you?
Very
good. Sorry, I just muted us.
And stable platform. So people
I just
can
have a
start getting
problem
into
right now. The
longer
weather
photos.
here has been
A lot of people are
pretty
just
bad.
doing these 1 minute
And
shots, and then they stack
I'm just
them.
hoping that it'll
And
clear
it's-
tomorrow.
the thing
Last
is
2 days it's been cloudy.
You want to get 5, 10, 15-minute shots.
Okay.
But when you start doing that, your mount has to be
just gonna
very
keep us
accurate.
muted, okay?
A lot of mounts can't do
Okay,
it.
sure.
And all you can get away with it is like maybe 1 or 2 minutes. And our mounts, you can go into 15, 20, 25-minute shots with it. And that's, I think, what will keep the industry going, because people get tired of looking at the same 1 minute photo stacked, 60 frames on it, because you just can't go deep enough and get a lot of information out of the photos. Just taking a lot of short pictures. You're missing a lot of information, and especially if you're getting into H-alpha type things where your photos are going to be, 40 hours by the time you're done with them, and I think that's what will help, keep the industry going. What I love about astronomy really is the mechanics. I love building mounts and constantly working on them to make them better and better and better. We've been building mounts now for 36 years, and so have a little bit of background on that. So it's a professional tinkerer, building go-karts and just taking machine shop in high school, and all that is just really just a love of machining, and never took any mechanics courses or engineering courses. It's just all from trial and error, and just a constant work in progress to make them better and better. My goal is mainly to make a mount that is extremely accurate, and it will just stay that way because it's machined accurate. We don't try to use any kind of, systems that will compensate for errors. We try to machine everything so there is no error. That's my main goal in the mount industry. So I love the mechanics of old equipment because they just make things do the most incredible stuff with just mechanics. They don't have solenoids or it's just all just hard mechanics. You know, it's like a weight drive system for the old telescopes. It's just this weight-driven mechanism, and that's what all these are. They're all systems that are mechanically incredible, and the people that have designed them were just brilliant. I think quality is, I like the way old stuff is built because it's still here and still working, and it's 100, 125 years old, and I think that's influenced me in making products that are going to last you a lifetime. And also, I try to make it visually pleasant to look at too. I don't want it to look like, you know, a casting or something, because we don't cast, we machine everything, and so I want it to look good. And that's what I get from older equipment, that, you know, antiques that I buy, is they're beautiful. You can just stare at them. You don't even have to use them. You can just sit there and look at them all day. About 1998, 99 area, and I was at a trade show, NAB in Vegas, which is the National Association of Broadcasters. It was a film show, and there was a company across the way that was making this 8-axis motion control system, and I knew one of the guys there, so I went and talked to him, and I said, "Oh, where did you get the electronics from?" Because I wanted to come out with a servo system for our mounts. And he said, "Oh, this gentleman right here in the booth built it for us," and all. And so I talked to him, and he was into astronomy. So I hired them to make up the servo driver system. Problem is, it had no smarts at all. It was just a servo system to run motors. Then, just out of the blue, couldn't have been more than a week after the show, I get this email from a gentleman in Germany saying that I'm designing a go-to system for your mount. Would you be interested in it? And I emailed him back in one of my long emails, as usual, saying yes. And about 6 months passed. I got the servo drive system from the company. A week later, I get an email from him saying, "Okay, I finished it." And I said, "Is it servo or is it steppers?" And he says, "Steppers." And so I told him, I said, "Oh, I have a servo system. Can I send it to you and see if you can get the two to talk to each other and work?" And I said, "I'm going to be out there actually in a couple of weeks doing a trade show in Munich." And he said, "Sure." So 2 weeks later, I met up with him, stayed at his house for about a week, and played with the system, and it was unbelievable. And from there on, he's been constantly doing all the programming for it. And so, and the nice thing is if there's something somebody wants, says, "Oh, it'd be nice if this go-to system did this," I just email him and say, "Can you do this?" He does it, and you just download it into your Gemini, and it's going. And they've just been upgrading the electronics, mainly because after about every 10 years, you can't get the parts anymore, so you have to just change to new electronics. And that's why they're where it is now. It has nothing to do with it's better, it's just couldn't make it the other way. But they constantly get better because the programming's better, the chips are better, and all, so. That's a C6 F8, built in 1969. They only made 50 of them. It was nice that they picked our plate to become the standard, and it's probably because we were the first ones out with a system, and it just made it, I think, so much better for all the astronomy people out there that they did decide to stick with one side and size, and everyone just basically copied it from us. But it made it so much easier because now people can interchange their telescopes and all that. And so it's, I don't look at it really as an achievement or something. It's just, it was nice that they picked us, but that's all I can say on that.
Warning! Warning, my foot, be still, you bobblehead.
Look, it went on.
Rush. Kill. Destroy.
I like Lost in Space TV show. Just thought it would be so neat to be able to fly around there, and I think that just got my interest in the stars and all that, because every time I look up to the stars to this day, I just would love to see them find life somewhere else, you know, any kind of life. And just a dream before I die that that happens.
Okay, ladies and gentlemen, we are back. Sorry, I didn't press the right button there for a second, so I don't know if you guys heard me, but you know, that's what happens when we do this kind of stuff. So right now we have Christopher Go, and he is going to be talking about planetary imaging. So this is like the complete opposite of what Adam was doing. And if you can kind of see in your corner, somewhere down there and over here and everything else, we're going to get started. So Chris, can you hear us? Yeah, can you guys hear Chris? Uh-oh, we lost him. Are you there, Chris? Say something. Uh-oh, minor hiccups going on here. We'll get his audio back up in just 2 seconds. Have you been, Chris, have you muted? We can't hear him at this exact moment. Give us 2 seconds, and we're just going to quickly figure out what's going on.
Can you hear me? Can you hear me?
Oh, there we go. There we go.
Okay. Okay.
All right, talk, Chris.
Can you hear me?
Yep.
Okay, good.
Can everybody hear Chris right now? Give it a couple of seconds for it to catch up on the live stream. There is quite a delay, so. All right, Chris, you're good to go. They can hear you now.
Okay. Perfect. Good morning, everyone. So I'm going to have a 3-part talk. The first part will be an introduction to modern planetary imaging. The second part, we're hoping tomorrow, if the sky is clear, we're going to have a live imaging session I'm going to go out there, image. We're going to image Jupiter, and if we have time, try to image Mars in the time frame. So we're hoping right now it's totally overcast here in Cebu, but we're hoping to have clear skies tomorrow. If not, we might have to move it on Sunday, but we'll just see. And the third part of my talk will be we're going to do a live processing. So hopefully everything will cooperate, including the weather. So we're going to do an introduction to planetary imaging. Well, basically, when we're doing planetary imaging, we're basically fighting the atmosphere. Um, well, this is our only problem. We have this atmosphere which degrades image. Unfortunately, we cannot live without the atmosphere. So we try to find ways to overcome this problem. So the first way is getting out of the atmosphere. So we send spacecrafts. The second one is adaptive optics, which was developed a few decades ago. Firstly, by the National Security Agency of the United States to spy on Earth, and it was declassified, and the technology was given to astronomers, and is currently used by big observatories. Unfortunately, the first two technology is rather way out of our budget. A lot of these cost, getting out of the atmosphere would cost billions of dollars, while adaptive optics right now, there's a guy in San Diego, Don Burns, who's actually developing amateur scale adaptive optics. Unfortunately, the price is still, I think he's quoting around 50K for the adaptive optics. Well, the method which is affordable for us is lucky imaging. So what is lucky imaging? So basically what we're doing is we're capturing videos of the planet using high speed, highly sensitive videos, and using software to basically sort out the good and the bad and stack them. So the development of lucky imaging came about with, first of all, inexpensive video capture device. We started with webcams. I remember, I think, what is it? More than 15 years ago, we were starting to use the 2U cam, which was the first planetary cam that was used. I think some imagers were also using the quick cam. Then came the security cameras from different manufacturers, like the Imaging Source, or a lot of these companies were making security cameras, which we adopted to Astro use. And finally, right now, we have some companies, astro camera companies, that are making dedicated planetary cameras. Now, there's another important advancement, which is the computer interface, computer hardware. We now have very powerful computers. I remember before when I started, when I had my first computer, the only thing the fastest interface we had was the parallel port. We had a serial and the parallel port, and these interfaces are not enough to gather the data or absorb the data that the modern cameras have. Right now, most of these cameras use USB 3, which can transfer a lot of data into your computer. And the most important development really is the development of software control and processing software dedicated for planetary imaging. And one thing amazing is that these softwares are free. Control software like fire capture and processing software like AutoStacker and Registax, which we use. These developments really helped out in the development of planetary imaging. Now, to choose the right equipment, there's a lot of consideration that we have, but any equipment is capable of basically imaging the planets. But well, some equipment would be better than others. The first is the telescope. The bigger the telescope, the more data you will get, the bigger resolution you will have. When I started imaging, actually, I used an astrophysics 130 EDF. It was an old astrophysics oil space refractor. And in one of those, I remember it was during the time of the Great Mars Opposition in 2003. We were having a uh, in one of the universities here in Cebu. We had a public outreach where we showed the the public Mars, and I set up two telescopes. The first was the AP-130, and the second one was a C8. Then I had a comment from one of the people who was observing, and they said that the C8 is getting better image than your the refractor. This wasn't expert amateur astronomer, but the ordinary public, and I was wondering, are you sure? This AP refractor cost 6 times more than my C8. So I went there and looked, and true enough, the aperture rules. The C8 had better quality, so I switched from imaging the C8 to the from the AP-130 to the C8, and basically for the past couple of years, I upgraded to the C11, and right now I'm using the C14. So basically, why do I choose the Schmidt-Cassegrain? Um, well, you can actually use Newtonians. A lot of imagers like Anthony Wesley, Phil Miles, they use Newtonians. But the thing is, the Schmidt-Cassegrain, these are compact telescopes, and mostly the quality of the C4, the Schmidt-Cassegrains, you only need a small area in your chip to basically um, to image. So as long as the center part is good, then usually you'll have a good quality image. I've been lucky because my three Schmidt-Cassegrains have been good. I've been getting good images with the three of them from the C8, 11, and the 14. And it's easier to mount because of the compact design. And you do need, because of the magnification that you're using, you need a good mount, a solid mount to do planetary imaging. Now, the cameras, when we started imaging, we had a webcam, but right now, very few people use the webcam. There's a lot of inexpensive high-speed cameras available, especially from QHY and other companies. These are affordable right now, and with very powerful interface. One thing you should be wary about webcam is that because it's used to run image through the internet, a lot of these webcams actually compress data. And this is a problem because when you compress data, you lose a lot of data because, well, it's just the nature of webcams that they have to course through the data through the internet. So to save on bandwidth, they try to reduce the amount of data. While the high-speed cameras, you get the full force of the data. You can get actually basically everything. So you probably get better quality image with a high-speed camera. Now, a big question is, should you use color or monochrome? There's a big problem when you're imaging planets, especially when the planets are low. Anything below 70 degrees altitude, what happens is you get atmospheric dispersion, which means that the three colors will not focus on the same plane. In a sense, that's the reason why a lot of people use monochrome cameras right now. They use filters, RGB filters, to recreate the color. But by using separate RGB filters, you basically are able to basically compensate for atmospheric dispersion. But right now, there's a device, it's called the ADC, which ZWO sells, the atmospheric dispersion corrector, which basically helps color cameras to basically overcome atmospheric dispersion. Personally, I haven't used the ADC, but I've heard a lot of people being able to successfully use this with the color cam. Well, the color cam is much easier, and I would recommend it to the beginner, for the beginner. But unfortunately, right now, the two major planets, especially Saturn and Jupiter, are on the southern hemisphere, and Mars right now is still on the southern hemisphere until basically later this year where it will slowly move to the northern hemisphere. But for the next probably next 4 years, the Saturn and Jupiter will stay in the southern hemisphere. So you will need something to compensate the atmospheric dispersion. The ADC will help, and also if you really want the best image, it's really going monochrome is really the best. But the thing is, monochrome is far more expensive because not only is the monochrome camera more expensive, which is funny because you would think that color TV and a black and white TV, black and color should be more expensive. But in the case of these cameras, the monochrome is actually more expensive than the color cameras. Plus, you have to buy a filter wheel and the filters to basically create the color images. But it's a complicated setup, complicated processing, but you get the best image with a monochrome camera. Now, one thing you should bear in mind also with these cameras is that you should check on the interface. Make sure it's USB 3. A lot of older cameras use USB 2. Probably if you're using ROI, that might not be a problem, but when you're imaging the moon or the sun, the interface would really help a lot. Having a fast interface would be very important. But most of the new cameras are USB 3, so this should not be a problem if you buy a more recent camera. Now, another problem with the color cam is if you look at this image, you'll see grids. Technically, the monochrome camera is more sensitive than the color cam. And this is because it doesn't have those Bayer filters. The Bayer filters are what creates the color. So each pixel of the monochrome camera has about 4 filters. Basically, it has its own RGB filter that basically recreates the color. And if you look at this image closely, you'll see some grid lines in the image. So this is the Bayer lines. This is basically the space between the filters. And this is a big problem with the color cam. And one thing you should also bear in mind, because one thing about color cams is that when you're going into RAW mode, RAW, RAW mode, the image will look black and white. It'll look monochrome, but it's actually color. And you have to re-extract the color when you're basically stacking in AutoStacker or using another software to convert the RAW into a color image. If you're using a more color cam, I would always recommend RAW because it gives you the best data for capturing using a color cam. But in the end, this is an image using a color cam. This is actually image using a Celestron Next Image 5. So this is a very old camera, USB 2, which I used. I tested a couple of years ago, and even with a color cam, this is with my C14, can get a respectable image. It's actually a good image. So but the thing is, when I took this image, Jupiter was 80 degrees above the horizon. So it was basically close to overhead. So I would, in the end, really, if you want to get the best image, get an ADC or get a monochrome cam with the filters. Now, these are other things that you will need. For those of you who were imaging before with film, I remember we were using eyepiece projection when we were imaging planets. In the case of the CMOS or digital imaging, you only need a Barlow because of the small pixel size of the cameras. Right now, I use the Astrophysics Barcon, which is a variable Barlow. I like it because I can basically play with the magnification depending on the distance between the lens, the Barlow lens, and the camera chip. It's quite flexible for me to use this Barlow. You don't need eyepiece projection anymore when using digital cameras. If you're using a monochrome camera, I would recommend a filter wheel, a motorized filter wheel. That will basically a motorized one is better than a manual one because when you're imaging planets, you want to image as fast as possible. Then the filters, the RGB filters, and some very important scientific filters like the infrared, UV, and the methane band. Of these, the methane band is particularly important because a lot of special features, especially on Jupiter, like high altitude clouds or impact remnants, are bright in methane band. This is I think this is a more expensive filter than most filters, but they give a lot of scientific info on the planets that we capture. One thing about the methane band is it's a narrowband filter, so you'll probably need to basically image like the way you would image deep sky. So you have to take dark frames. Anyway, we'll go over it tomorrow when we do the actual imaging. Another important accessory I would recommend is a flip mirror. I know it's difficult to find flip mirrors now, but when you're imaging at 3 or 4 in the morning and your brain isn't 100%, it can get frustrating getting that small planet into the field of view of the small chip of your planetary camera. So it would be good to use a flip mirror, so things will be easier. It'll take you seconds to find the planet. And another important thing that you will need is a motorized filter wheel. No, this motorized filter wheel basically, especially, no, motorized focuser. I'm sorry. The motorized focuser, I would recommend the Crayford focuser because if you're going to use the mirror focuser, you're going to have image shift. And when you're having a basically the small image window of a planet, and it's difficult to keep the planet in the field of view when you're focusing using the mirror. So a Crayford focuser with a motor would really help, and it's very important to achieve the fine focus. It's easier to do fine focus with a motorized focuser than doing things manually. And the last accessory I would recommend, I know it might look minor, but actually for me, this was a very big help, is the vibration suppression pods. If you're imaging on concrete surfaces, especially with surfaces with a lot of vibration, the VSP, there's, I think Celestron sells these. Other companies also sell these. They are very important. In my case, they basically convert high frequency vibration to low frequency vibration on hard surfaces. In my case, I use image on a veranda, which has a lot of vibration. And I would say it basically helped maybe +2 on the seeing scale in improving the image using these vibration suppression pods. Now, the location for imaging, here are some things that you have to bear in mind. Location is very important. Of course, you know what's the best place to image planets? It's to be on an island close to the equator, close to the sea, and with winds from the sea. But there are other things that you have to also bear in mind, like stay away from heat sources. Right now, it's not a big problem early in the morning, but when you're imaging in the evening, hot roofs can basically degrade images. And another thing is heat sources like air conditioning, heaters. These things can degrade image. So if you can stay away, even your floor, if you're imaging on a concrete floor and it's hot, especially on early evenings, what I normally do is I basically spray it with water, basically hose it down the floor just to cool it about 3 hours before imaging. So it's important to keep these little things perfect because it's not always that we get bad images because of seeing. Next, we need to cool the telescope. The C8 small telescopes, it's easy to cool. But if you have a bigger telescope like my C14, it takes about 2 to 3 hours to cool. So I had to, spend time to cool the telescope. Then, of course, collimation is very, very important, especially for Schmidt-Cassegrains or Newtonians. Now, when you do, especially when you're imaging with Schmidt-Cassegrains, and you have to collimate on camera because there's a little flexure, there's a slight flexure when you're, especially with your filter wheel, the Barlow, plus you have the flip mirror, there's a slight flexure which can affect collimation. So you have to collimate in camera with with the object that, or in my case, I don't actually collimate with the planets, especially when they're low in the sky. I would choose a star about 70, 80 degrees above the horizon, and hopefully when there's good seeing, I actually collimate there. So far, I've been lucky. For the C14 that I have, I don't have problems with the flexure as it moves around the sky, whether in the north or south latitudes, uh, or declination, north or south declination. I don't have a problem with collimation. My telescope seems to keep collimation even as I move throughout the sky. So I'm not sure with yours, but if your telescope does have a flexure and changes its collimation, you may have to recollimate it to where your target object is. If you want to collimate on, let's say, Jupiter, I would recommend one of the moons like Io or Europa. These will be good targets for collimation. All you have to do is to basically put the moon slightly out of focus and basically collimate from there. Uh, Another thing is you have to plan your imaging session with WinJupos. WinJupos has a software. It is a ephemerides where you can see the position of the moons, whether the great red spot can be seen. So having preparation, you'll basically know what you're imaging. Now, for capturing, there's a software called Fire Capture, which we use for capturing. Um, for now, this is for me the best software to use for capture. Not only does it control your camera, it controls your filter wheel, even your telescope. It has an auto guide function that basically can keep your object by controlling your telescope, keep an object in the center of your field of view. Right now, it can support probably a few dozen cameras. It's quite flexible. And one thing I like about this camera, it has a feature which basically what it does is you can use your RAM as a buffer for your camera. This is important when you're imaging the moon, when your hard drive cannot keep up. Oh, by the way, talking about hardware, something which I forgot to talk about is the hard drive, which is very important part of your imaging computer. Right now, there's hard drive and there's solid state drive. For planets, the hard drive can work without a problem. But when you're imaging the sun or imaging the moon, you will probably need a solid state drive to basically be able to get the data that the camera, or for the camera to basically, for the computer to keep up with the data that the camera is sending it. So a solid state drive would be an excellent choice. The thing is, Fire Capture has a feature. I'll show it tomorrow when we're doing live imaging. It's a little complicated because you have to basically include it in the startup of the program. Basically, assign specific amount of RAM to from your memory as a buffer for Fire Capture. So using this would really help a lot to basically help you basically have less drop frames compared to if you don't use a RAM buffer. You actually have to, anyway, I'll just show it to you now. Here, it's actually on the startup. So you go to the where you're going to start and properties, and there you have it. I wonder if you can zoom it. So basically, you have to add this. Where was that? Where was the notepad here? Or let's just use Word. So you have to add these two. Now, the number 9 is 9 gig. So my laptop has about 16 gig of memory. So I basically assign these two actually, I think S is minimum, X is maximum. So you have to assign these two, how much RAM you want to dedicate um, uh, for your imaging for file capture as RAM buffer. So just add these two commands to the command line of fire capture. Basically, you add it here in the property section here. So when basically fire capture launches, it will basically dedicate those RAM as buffer. So yeah, here it is again. So just use this command uh, for the buffer for fire capture. And let's go back to the talk. And lastly, about the fire capture, it has a make sure the focuser, the filter wheel, the mount is all ASCOM compatible, because this is very important. Basically because uh, uh, fire capture runs on ASCOM. So make sure that the device that you have has an ASCOM driver. And lastly, one thing nice about fire capture is it's free, so you can download it anytime. Now here are the controls, basic controls of fire capture. It's basically exposure and gain. These two basically make the image brighter, but there are pros and cons. The exposure would control your frame rate. So the faster your exposure, the more frames you will be able to capture. Basically, your frame rate will be 1 over your exposure time. So let's say you're doing 1 over 10 seconds exposure, so you'll get a frame rate of approximately 10 frames per second. For Jupiter, I actually capture about 1 over 100 seconds. So basically, it's about more or less about 100 frames per second that I'm capturing. Now the next is the gain. The problem with the gain is the higher the gain, the more noisier the image will be. So you probably have to play with the exposure time and the gain. Um, uh, Another thing that you have to use, especially with the cameras these days, is the region of interest. Again, I will basically demo this tomorrow, uh, since we'll have more time, and we're doing the live demo on how to do the ROI. ROI, basically region of interest. Basically, you're reducing the frame of the camera, because most planets are very small. Now, why is this important? Three reasons. First of all, you get faster frame rates when you're using ROI, because the camera is sending less data. Second, you have a smaller data set, so in case you want to back up in the future, your data is smaller. And because your file size are smaller, when you're processing it as auto stacker, processing would be a lot faster. So these things that you have to bear in mind, when you're using ROI. Now, a lot of people are asking, should we use 16-bit or 8-bit? Uh, well, I've been using 8-bit for years. I know some imagers use 16-bit. For me, I like to use 16-bit, 8-bit, because the file size are smaller, and I don't see any image difference, the quality-wise, especially when you're using very high gain. I don't see a big difference between 16 and 8-bit. Basically, for me, in my opinion, 8-bit would be more practical. Of course, 16-bit is better if you have more time for processing, but practical wise, 8-bit is good enough. Now, an important step, especially since right now, when we're imaging planets, there's another extra step that we're doing. One problem with planetary imaging is that there's a limited amount of time that we can give to capture each frame. And the reason is because the planet rotates. The rotation of the planet sets a limitation on how long you can capture. So, but there is a way out of it. And WinJuPost, which is a software, basically um, uh, uh, basically helps us overcome. So one thing you should do is there's this here WinJupos file naming convention. You have to press this and basically activate this WinJupos naming convention. This will help you when you're doing imaging, when you're doing processing with WinJupos, which I will demonstrate this Sunday. And what are the capture secrets? You know, a lot of people were asking me, what's your what exposure time are you using? What are your settings? Tomorrow you will see that it's not a simple answer because it's just like when you're asking what gear should you use when you're driving. Uh, Basically, my settings change every night depending on transparency and seeing, and mostly because of transparency. But basically, you have to find a sweet spot on your setting. One thing I would always recommend, use the fastest frame rate possible without going over 400 dB. This is for the camera that I'm using, the 290 QHY 290. Don't go over 400 dB. But in some cases, like Saturn, I do sometimes go over 400 dB. But using it's a good rule of thumb for using basically an exposure time where you don't go over 400 dB. Again, in gain, uh, turn off gamma, and when you're basically imaging, spend time to focus. A lot of people are asking, what's the secret for focusing? Yeah, honestly, when seeing is good, it's easy to focus. But when seeing is not so good, focusing can be a challenge. What I do is a method called jogging. So basically, what I do is basically go in and out of focus, and basically try to find the midpoint. It's easier to do when you're using a motorized focuser. So you'll know how many clicks you have to do when you go basically where you're in the center, you go out, and when you go in a sense that you can basically judge what the midpoint is by counting how many clicks that you need to go in and out of focus. So basically, that's how I do my focus. So far, it's been an effective method, but usually when the seeing is below 5, it's really, really tough to focus. Next,
Chris, real quick. So somebody's asking, why should you turn off the gamma?
well, basically, one thing about gamma, it doesn't really add anything to your image. And one thing I realized that basically the contrast is less when you turn on gamma than when you don't use gamma. Is that it?
Yeah, that was it. Sorry.
Okay, no problem. Lastly, one thing about the final image quality depends on all the small details that you do, from basically the preparation that you have, the location, the cooling of your OTA, the collimation, um, uh, the seeing. Of course, it's always easy to say that you get the best image when the seeing is good, but we don't always get good seeing. So we just try to live with what we have. So if you get everything perfect, those little things perfect, it helps in getting a better image. No matter how bad your image is, it's difficult to get data or good quality image if your raw image is bad. Now for image processing, what I normally use, right? Well, basically the standard software right now is AutoStacker. Uh, Emil has created a very good software for stacking, and it has multi-point alignment. I've used it for many years now, and it's far superior than Registax that we were using before. A lot of it. One thing about AutoStacker, it's very easy to use. Again, we'll demonstrate how to use it on Sunday. And one thing, or Monday, or yeah, Sunday your time. I'm sorry, I'm a little confused because we're right now one day ahead. Uh, we'll talk more about it on Sunday on how to use this AutoStacker. Uh, One thing, so I would recommend that if you can, just download this software ahead of time so we can demo it, and you can also try it yourself while we're doing the demo. Uh, One thing nice about AutoStacker, it can do multiple. You can process basically multiple files at the same time. So what I normally do in my schedule, in my workflow, is after imaging, especially when it's still in the middle of the night, I basically copy my image to a removable hard drive or my data to a removable hard drive, and basically move it to my desktop and just have the desktop process it until it's done. And when I wake up in the morning, the data is ready for me to work on. So one thing nice about the multi-point alignment is that you can get better quality data on each region, especially when you're using very, very high power. Seeing tends to be different on different areas of the planet. Anyway, we'll discuss more of this on Sunday. And here, Registax, Registax can never go away because of this feature called wavelets. Wavelets is really magic for me. You can see that you have to have the correct or sweet settings on the wavelets to get fantastic image. A lot of people I see, a lot of their images look blurry because after stacking, the image does look blurry. You have to use Registax to basically draw out the image, and getting the right settings is very important. And again, we will be discussing this more thoroughly on Sunday on how to basically process these data. It's a very good sharpening tool. Then lastly, when you're doing monochrome, normally we do red, green, and blue. We use Photoshop to basically merge these images. Again, I will show this on Sunday on how to do it step by step on basically doing this RGB merge in Registax. And lastly, after processing everything, of course, there's also WinJupos. I'll talk more about it on Sunday because it's easier to explain doing a live demo than basically talking about it. But one thing about when you're doing WinJupos derotation, bear in mind that when you capture sets of data now, not just a single RGB. What is derotation? Derotation is basically stacking on steroids. It's basically stacking with while overcoming the rotation of the planets. So what WinJupos would basically do is basically convert the planet and basically align it on the central, basically the meridian. So each meridian point will be merged by WinJupos. So basically, you overcome the rotation, and so as I said, it's basically stacking on steroids. It changes the way you capture because right now, instead of just doing RGB, then the rest of them, you would all actually capture a set of RGB. I will explain this tomorrow when we're doing the live imaging on how on why we do it and how many that we capture. We'll get more info on that tomorrow. Again, when we're doing final processing, it's actually a fight between sharpening and noise reduction. For sharpening, we have a Registack wavelets, and there's a software called this is actually it used to be a free software. Google bought it a few years ago, then DxO bought it. It's now a DxO Nix. There's a free version of this software that you can download. The newer version is paid version. You might want to test it. This is a plugin for Photoshop that you can use for basically sharpening. We'll demo this on Sunday. I will show you how to use this on Sunday. And for noise reduction, there are two tools in Photoshop. This is the speckle and dust and scratches that are very useful in noise reduction. And finally, right now, when you're doing the final image, there's a lot of debate, no, north up, south up. But right now, because we're doing a lot of support for NASA spacecraft, we're doing everything north up right now. So this is basically the convention for which NASA is asking. And of course, you save everything. We use UT time. So everything will be the same for all imagers, the universal time. Uh, it's also recommended if you're using, especially when you're using derotation, to indicate the amount of time that you use to capture in derotation, and get the central meridian information. This is helpful in knowing where in Jupiter that you're observing. Um, Again, for Jupiter and Saturn, you need the uh, three central meridian info. For Mars, there's only one. And again, oh, you need information for the name. You include your name and location information. And basically, I'll add something, because this was supposed to be a basic talk. I think you'll probably find this information important. Let's wait a sec. Sorry. Now, I think you might find this information important. Now, when you're capturing planets, and I'll more or less demo this tomorrow. Uh, what's the most important thing that you determine your exposure time or gain? This one, the histogram level. You see this histogram here. Make sure it's close to as close to 100% as possible. But the problem with CMOS cameras, the capture is a very the histogram would jump very fast. I would recommend, as long as you keep it between 89 to 95%, as long as it doesn't get to 100, the closest that you can get before 100, you keep the histogram level at that level. Why do you need the histogram high? It's just like, when you're imaging, each of those pixels is like a glass of water. This glass of water. So you want that water to be as full as possible. So that's why why when it's the fuller it gets, as long as it doesn't overflow, the better contrast you're going to have. So as much as possible, keep the histogram level very high. There's also a problem when your histogram level is too low. You get that onion ring artifact when you're after stacking and you apply uh, uh, wavelets on the edges. You get that onion ring effect. So to overcome that, keep the histogram level high. Be mindful of the integration time, because Jupiter rotates very fast. In my case, for the C14, I limit each frame to be 30 seconds. For the C11, 45, and 1 minute for the C8. So for focusing, one thing nice about Jupiter, it has these two moons that you can use for focusing. Io and Europa would be perfect target for focusing. By the way, here's a secret. Of course, I'll show it tomorrow. When you're focusing, focus on the green filter. If you're imaging in monochrome, focus on the green, because well, if you get a good green image, then basically you'll get good. Do I change focus? There's a focus difference between the blue and the green, and it's a problem unless you have a basically focuser that is controlled by fire capture. I would not recommend that you change the focus on blue. I know it might be it might sound heresy for some imagers, but the blue data isn't really that important in the final scheme of things. As long as you get good red and green, then you get a good data. Next is when you're imaging in methane band. As I said earlier, methane band is a narrowband filter. It's like doing deep sky imaging. You need slower exposure times. In fact, you need binning to be able to capture good data in methane band. Because of the smaller size of the image, because of binning, I actually capture methane band up to 2 minutes. And like when you do using deep sky, when you're imaging deep sky, you need to actually take dark frames. And it's not just one single dark frame. I mean, the minimum is 5. Probably that would be a minimum 5 frames video for the dark frames, and you basically have to stack it in Registacks. I will basically demo this on Sunday. Oh, for Saturn, when you're imaging Saturn, the only way to get images like this is using WinJupo's derotation. The image that you're looking at right now is close to, I think, 50 to 55-minute capture. That's 50 to 55 minutes of data sitting out there capturing just for one image. The problem with Saturn is Saturn has very low surface brightness, which means that you need more time to capture, more data to capture to give it basically good quality. If you notice in this image, a lot of low contrast features can be seen. Here you can see some spots on Saturn, which you will never see if you're not using derotation. Again, when you're imaging Saturn, use histogram from 80 to 90% histogram. And use high grain, high frame rate. Now, earlier I said that you have to max out at 400. When I'm imaging Saturn, my blue is almost 480 dB or 48 dB. In QHY, the settings they have is in dB. And one thing nice about the QHY camera, it has actually, unlike other cameras which basically limit to 480 dB, you can actually go beyond 480 dB, although I would not recommend it. But sometimes you might use it, especially with faint objects like Saturn or Uranus or Neptune, which basically would require faster grain. One thing about exposure time, especially when you're seeing is not very good, you may have to use fast exposure time. So it's basically a play between exposure time and gain, and to overcome the noise of the gain is, well, the only way to overcome it is to capture more image. And lastly, Mars. Mars would be great for the northern hemisphere this year. Although 2 years ago we had a great Mars, we had a respectable, a very nice Mars opposition. The problem with that opposition was that Mars was way south, even for me. During that time of opposition, Mars was only about, I think, 50 plus degrees above the horizon here in Cebu. This year it'll be much higher because it'll be in the northern hemisphere, which will be a great opportunity for you guys in Europe, in North America, in Japan. This will be an excellent position. Mars will be in excellent position, and the size of Mars is quite respectable this year, probably around 22 arc seconds, which is basically just 3 arc seconds less from maximum. So this year would be best for Mars. Now, when you're imaging Mars, here are some one thing you should bear in mind. Please check your RGB filters, especially the blue filter. When I started imaging, I was using filters from Edmund Scientific, and I had a problem with their blue filter because their blue filter had an IR leak. So my Mars image were horrible during that time because of the blue. I couldn't get good blue. So when you're imaging with the blue filter on Mars, you should not be able to see, or the details, the albedo features should be very faint. The only thing that you should be seeing on blue are clouds. So just keep that in mind. That's why when you're imaging with blue, have the histogram only at 70%. Make sure that the surface is dark, but all the bright spots are the clouds, the morning, the afternoon clouds, or the poles of Mars, the ice caps of Mars, or the polar hoods of Mars. These are the things that will be bright in blue. So these are the things that you should see in your live capture. For the red and the green, again, it's 80 to 90%, not as high as Jupiter or Saturn. Um, One thing about Mars is that it rotates slower than Jupiter and Saturn. So you can actually have up to 4 minutes capture time for Mars. And make sure that, again, you have an IR block on your filter. Okay, so so far, do you have any questions?
Yes, there is quite a lot of questions for you. So let me just change this so we can see both of us. Where do I start? So the first question here, and this is actually an interesting question for AutoStacker. Should you use fewer larger squares, or should you use many smaller squares? Now, I have my own opinion on this, but I want to see what you say for this one.
Well, it really depends on the object, how big your object is. Well, let's just do a sample here. Where's AutoStacker? Okay. So this is last night's data. You know, for this size, you don't have to do the smallest size as possible. In my case, I use 104, and I only use Place AP. I don't actually do this manually. I do everything automatically. Well, it depends. For this one, I would use 104. When I'm using the methane band, because you know the methane band is smaller, and if you use this, you don't really get a lot. I usually go down to 48. So it's basically, it depends on how big on how big your capture is.
So usually when I do the sizes of the squares, and I do a lot of solar imaging, what the size of the squares actually can help determine here is the actual tessellation. So when you stack one image on top of the other, even though the actual circle of the whatever it is you're looking at, the moon or the sun or whatever it is, fits within the same field, different parts of it ripple at different points. And what I found here is on, you know, things like the moon, if I have a smaller grid size, it'll actually watch what the tessellation does across the entire surface over each image. And what happens here is the reference frame actually looks at all the other ones and then says, right, that one needs to come this way, that one needs to go that way, that one needs to go that way. So what happens here is if you don't actually have enough of these squares, or they have a bad placement, you will actually notice when the stack comes out, you'll have this strange smearing in certain areas where it's like shifted and like weird things happening. So again, the principle still works within the planets, but you don't want to go nuts. That's the important thing.
Yeah, I don't think getting, you know, as small as possible would be useful for the planets, because
no, definitely not.
No. It's basically you have to play on how big the size of your capture is. So I would go. It's not really smallest or the biggest, but somewhere in between.
So next question is vibration suppression pads. Are those for reducing vibrations from the environment or from the equipment itself?
No, that's for the ground.
Okay, do you want to explain why you would use a vibration suppression pad in general then?
You know, I live, especially when you're imaging in concrete surfaces. You know, my floor vibrates. So what those vibration suppression pad does is it converts the high frequency vibration to basically low frequency, which the lucky imaging can basically overcome. So basically, it reduces the amount of floor vibration.
Okay, so next question for RGB sets. What is the integration time window for planets like Jupiter?
I think I explained this earlier.
just in case they missed it.
Okay, it's 30 seconds when you're, well, it depends first of all on the focal length and the telescope size. So there's, if you're using a smaller telescope, you can get longer. For the C, as I said, for the C14, I'm using 30 seconds. For the C11, 45 seconds, and the C8, 1 minute. So basically, yeah, that's with a 2x Barlow.
Okay, I'm just going to ask this one question in reverse because somebody else asked a different question that would benefit from the first question being asked, which is, what about using 4K video capabilities of DSLR or mirrorless cameras? How do they compare to CCD CMOS?
Well, one problem with the these big cameras, I don't think you'll benefit anything for 4K. In fact, we're even using ROI. We're trying to reduce the frame. First of all, the planet, you can't act, there's a limited, the size of the planet is very limited. We can't really get huge like size of the moon for the planets, basically because of the atmosphere seeing. So one problem with when you're using DSLR and basically, I'm not saying that you cannot use it for imaging. You can use it for imaging. I know some people who are able to get good images for that, but the problem is that the files are big. The planets, when you're using the DSLR, you'll probably use 2%, 3% of the chip. You're not going to use everything. Basically, because the planets are very small, they're not huge, and it's not about the pixel size. In fact, the camera I'm using is it's basically
it's 2.9 microns.
Yeah, 2.9 it's 2.9 microns, but the thing is, it has a 1980 pixel by I think 1400 or something. But I only use I think 700 by 700 pixels ROI. So that's the only useful space that I'm using. So there's no using a DSLR, having that big frame will not benefit you. And the problem is also the frame rate because of the big size of the chip, and also the interface, whether you're going to burn it into your SD card, or remember, most DSLRs or mirrorless cameras, they only use USB 2. I don't think there's one that uses USB 3. So to transfer
the newer cameras will have started to use USB 3.
Yeah, well, if they use USB 3, and let's say you're using 4K or even at full HD, you'll probably get as high as how much? About if it's uncompressed, probably about 30 frames per second. Because if you go to 60 frames per second, you have to compress those data. I don't think even with my camera, which is about 2 megapixels at full frame, it can only do probably about 30, 40 frames per second without any compression. So I don't think I'm not saying that you cannot use a DSLR or mirrorless for planetary imaging, but it would not be ideal.
Well, so some of the older Canon cameras used to have a 640 by 480 crop mode, and in all honesty, the way I discovered planetary imaging was by using a DSLR. This is before I even owned any of these cameras, and I'd only just gotten into the hobby. And what I discovered here is, even with the 640 crop mode at 60 frames per second, my biggest enemy was actually compression. And the compression that they're using on these Canon cameras are just so severe that I used to get too many artifacts, and I'm forever trying to process these artifacts out, and it just never would work. So this brings me into the next question: is there any advantage of using a still set, even in RAW, versus doing video on a camera? Is it better to use the camera as a video, or is it better to do it in stills?
Well, you can actually use both. I know Anthony Wesley. I'm not sure if he's still doing it now. Before, he used to do still, and the only thing is, quality-wise, image quality-wise, there's no difference between using a still and video, because they're just two the same, just two different formats. But when you're processing, I think it's a bit messy when you're using still than when you're using video.
So here's an interesting question. And again, this is very subjective in so many ways. When you're imaging planets, and I guess when you're imaging anything in general, is it best to keep the gain down as low as possible, or is there an advantage to having a higher gain?
Well, as I said, what we're trying to achieve is the histogram level. Uh, um, it's a difficult question to ask. Of course, we would want to have as low gain as possible, but we get what nature gives us. It's not always that we get perfect conditions every day. So we need to fight seeing. We need to overcome transparency. That's why we use high gain. But the thing is, before we had a problem with gain, because when you're using high gain, you have a terrible image. There's no way to help it. But with derotation, it changes the gain. Example, the seeing is good, but there's clouds and the transparency, let's say, is about 10%. So what I do is, instead of capturing four images to get a good image normally on best seeing, I would capture 20. So in a sense, in the end, I'm still able to get a good image even with poor transparency, and salvage the situation and using high gain.
One other question here, and it's in reference to filters. I know this person mentions only just the one filter, but I would probably be better if we do it this way. So we're going to start with this. Mars, would it actually benefit to use a IR filter, or would it actually cause more of a problem?
What do you mean IR? IR pass or IR block?
That's the thing that the person hasn't mentioned. So the idea would be here is which one would be better suited, IR pass or IR block?
First of all, if you're taking RGB, the image has to be IR blocked, because if not, you'll get crazy problems. What you need is IR pass. For IR pass is you can get some details, but one thing I noticed, it's close to red. The image is close to red. Sometimes when you're seeing is not good, instead of using red, you can actually use IR for your RGB, like IRGB instead of RGB. Probably that's what he probably meant. But if you're taking basically color image, you want the IR blocked, while the IR has to be passed. Now you have to be very careful when you buy filters like UV, IR. This is one thing I discovered which really drove me crazy, and the problem is I lost a lot of money. One time I bought an IR filter, and I didn't know, but after I tried to image an object, and I was wondering what the heck is wrong. I was imaging Uranus with my IR filter. Why is it bright? Then I went back and checked the data for that filter. It had a UV pass. I mean, I bought an IR filter with a UV pass, or UV leak, and the other way around, I bought a UV filter which has an IR leak. So you have to be very careful when you buy an IR pass or UV pass filters. Make sure that it doesn't have a leak on the other end of the spectrum.
So can you stack filters together then?
The problem is we have a filter wheel, and I don't think it's that simple to stack on a filter wheel.
Yeah, no, I've had that question asked before. I mean, it is, in some ways you can do it. It depends on your camera setup and if you're using extension tubes and things like that. And there are opportunities to add filters within the path. But generally speaking, it's probably best not to use multiple filters of all different types then, I'm assuming, and trying to stack them on top of each other.
It's difficult because, first of all, when you add these filters, you lose light. which means you can, you basically have to use a slower, more gain or exposure time. And the thing is, most of the filter wheels right now are very thin filters, so there's no way to stack them. And the big problem is if you place it in front, we actually image UV and IR. So if you block these two, uh, you know, uh, what's the point? You have to remove it in between imaging. Uh, it's a lot of complicate. It has a lot of more complication. And later on, I will explain when we're doing processing why it's not good to touch your camera when you're imaging, because in
Excellent.
derotation, you want everything as is.
Okay, so this is actually a good question here. If all your SETs are the same focal ratio, obviously different sizes, and you're using a 2x Barlow, why is your integration times different?
Well, the telescope we can control, but Mother Nature we can't. So in the end, if there's clouds or thin mist and the transparency is low, I get low. I have longer integration time. When the seeing is good, I get less integration time. If the seeing is bad, let's say the seeing is about 5/10, instead of getting 4, I get 15 and stack less and derotate everything.
Okay, so for those
That's what I'm talking about. But the integration time probably is, different SETs, have different focal lengths. I think C8 is 2000, C11 is 2800, and C14 is I think
38,
3800.
yeah,
So
something like that. I think, but the F ratio is the same, like F9 across the board or something, or F10.
yeah, but the integration time is not about the F ratio, but how fast the planet rotates.
Right. Okay, so obviously the higher the magnification in this particular case, or the longer the focal length, really, should I say, the more apparent the movement is going to be, hence why your integration time is shortened. So, for example, Jupiter rotates once on its axis is what,
Every 10 hours.
5 hours, right? Which means that within a space of 5 and a bit hours, let's just say you could watch Jupiter from one side to the other, you can see it make one complete side from one end to the other. Hence, you can actually watch the red spot come all the way around and then end up on the other side, which is quite amazing. And there's plenty of people that have imaged stuff like that.
Yes.
So some of these other questions we're going to leave for tomorrow, and the reason why is they will get answered tomorrow. So real quick, what is the camera and the filter wheel that you like to use?
Right now, I'm using the QHY290, and I'm using Starlight Express filter wheel. I love this camera because, first of all, this is an interesting thing. A lot of people are asking me. I'm actually using the QHY290M. This is technically a cooled camera, but I never use the cooler. So you can actually use the small QHY3290 instead of the 290 with cooler. Why don't I use the cooler? Because when I turn on the fan, the whole thing vibrates and I get mush. So the image quality
that's
is
an interesting
horrible when you turn on. But why do I still use the cool camera? It's because of temperature. The cool camera has better, I think, basically hardware that keeps the camera cool. So my camera, I live in the tropics, so it's pretty hot here. And with a cool camera, my camera's temperature is around 30 degrees centigrade. With the other camera, with the uncooled camera, the temperature can go as high as about 50 to 60 degrees. So there's a 30-degree differential for temperature wise, which is a lot for CMOS and CCD cameras.
So for those of you out there, the 290 comes in two variants, which is the cooled and uncooled version. And as Chris was saying, he uses the cooled version, but without the cooling capabilities, which effectively turns the camera into a passive cooling system because it actually has a heat sink built into the back of it. And then
Yes.
obviously there's an active cooling fan that actually takes the heat away from the heat sink. But there's quite a few different designs of these cameras that I've seen with these types of things, which is also why we've done a special. So if you guys are interested in picking up one of these cameras, I believe we are doing a 20% off the entire package when you buy both the camera and the QHY filter wheel. So that's the 290 cooled with the smaller filter wheel. Is 20% off right now, coupled with the 10% off the chroma filters. So there is no reason, and you shouldn't even be waiting. Now is the time to actually get one of these cameras.
Yeah.
Any other QHY cameras that you recommend for doing imaging for planets and things like that?
Right now, I've only used the 290. I think for the color, if you want to go color, probably the 244 might be a good choice. A lot of people have had good images with that, with a 22. Is it 224? 224.
Yeah, 224.
224. Yeah, but in my case, my only experience is a 290, and the reason why I use it is because it's a back illuminated camera. It's basically the most sensitive right now available for planetary imaging. And what I really look at is the methane band, all close to the 900 nanometer, where it's very high in sensitivity, high in QE at that point in 900 nanometers. But for filters, I've been using chroma for years, and the reason is because it has very high pass through bandwidth, close to 100%. So
And they don't have UV leaks in them.
no UV leaks. One thing, you need everything optimized. You need as much light as possible. Some people say, I live in the northern hemisphere. The seeing is not good. Why should I use a C14? The reason is because you can actually stop down. Instead of, let's say, using a 2x Barlow, you can use it without a Barlow. And with the amount of light that you're getting, it's basically about the light more than the magnification. You can get higher frame rate and lower gain. It's all about getting more data, quality data, more light, to get the best image.
Excellent. All right, so we look forward to the demonstration tomorrow. We will give you guys a heads up if the weather is bad. So if the weather does turn bad or turn for the worse, we will basically do a different presentation. So we do have a backup for you guys just in case weather is not permitting. I don't know where everybody else is from here, but I can tell you now we've got a cold front coming in to California, or at least in Southern California, which means I was going to do something, but I'm not now because I don't want to be freezing cold out there looking at the backside of a cloud. So before we run away, this is your last chance to post any questions while we're still on. And like I said, we are going to be doing a giveaway. Right now, I have one $50 gift certificate available. And if you want to win that $50 gift certificate, you must subscribe to our YouTube channel and you must hop onto our Instagram account. All that information can be found on our website, telescopes.net. Just scroll to the very bottom and look for those icons. You must be subscribed to both our YouTube and our Instagram account. And all you got to do is send a direct message to us saying, I want to be a part of all of this. And we are going to randomly pick somebody out and announce who that is tomorrow. You do not need to be present to win. We will get your contact information and you will get your $50 gift certificate. So if there's no other questions, we're going to try and wrap this up. It is almost 6 o'clock our time, so we got about 8 more minutes left.
Okay, hopefully we'll have a good weather here because right now it's totally overcast right now. I don't know why it's supposed to be summer here. It's supposed to be dry season, but the last 2 days have been cloudy. So,
well, it's because we want to do something. That's why. Will solar imaging be discussed tomorrow? No, it will not. We don't actually have anything planned for solar during these next 3 days, but if you actually look at our previous postings, I actually went live during the test just so you guys could see what was going on. while I was testing this entire system, because this is very, very new to us. And I actually have a control center here, and I've got like too many screens. I've got the lights on me, and I'm starting to sweat now because of the heat generating from all this stuff. But yeah, so check out some of our previous images, videos, and it will show you some of the solar stuff. And if you guys didn't know, there actually is an active region out there right now, 2759, so that's AR 2759. There was actually a sunspot, and there's a couple of prominences, so it's well worth looking at. And hopefully we will see you back here tomorrow. Don't forget to check out our website, telescopes.net, or you can call us toll-free 888-427-8766. We will be open tomorrow to take your calls, even though the store itself is closed. The hours is Pacific time is going to be 9 till 4 tomorrow, I believe. So if you want to buy something, or you just want to talk to somebody because you're probably bored like the rest of us are, being stuck at home in this amazing coronavirus madness, feel free to give us a shout, and we will see you tomorrow. And ladies and gentlemen, thank you very much to Chris.
See you guys tomorrow.
All right, we will see you tomorrow.